Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. Had to stop by Don Does Math's studio there for a second, so sorry if you caught that. But yeah, Don's go live message was it 95% of people can't solve this puzzle, and it was an anagram. Obviously, my mind is in the gutter, Don. I believe it was that one. Obviously, it's spine. uh, Sorry, you got a Trivia League I play in online, and yeah, definitely didn't definitely did not submit. Good news, it is due at 6 in the morning, so I've got some time. Bad news, it's due at 6 in the morning, so I'm not getting up like just before it actually is due. Alright, so we are going to be dusting off our the Wacom tablet here, because we haven't actually done anything on it in a while. But I was inspired. We just got back from a family vacation to Wales. Beautiful location, by the way. If you ever get the chance, definitely recommend spending some time in, like, Yorkshire area over in Wales. It is quite pretty. Scotland is going to be coming up at some point. Going to be going to France and a few other places in Europe over the next few years, so it's going to be really great. And it's really awesome because everything is so close, like in terms of, or like comparison to the United States. If you want to fly from the United States to Europe, it takes a long time and it takes a lot of money. If you want to go from England to the rest of Europe, it's not so bad. And like, obviously, but at the same time, I hadn't really, thought of the economics of it that much until, we got here. So, loving it. Okay, so let me check my area that I can work with. It works. Okay, I saw on Twitter, and I will continue to call it Twitter, I don't care, there was a nice little question that said, it was... How exactly does the derivative of log base a of x work? Because this natural log just kind of pops out of nowhere. The hell did that come from? So I was able to kind of think about it for a second and then say, oh, right, I remember how to do this. Took a minute, but, a lot of people were saying, oh, well, this is just the, like, general or generalized form of the natural log of x being our derivative. We know what the natural log of x's derivative is. It's just 1 over x. So in this case, it's going to be similar to that, and then you do a change of base. Ta-da, we're done. And to that, I said, yeah, sure, that's fine. But also, let's try and think about it in a broader sense and think about how do we find the derivative directly of this particular logarithm with base a, not base e, specifically. And I said, all right, let's do this a couple of different ways. So one, we can think about change of base. So again, log base a of x is going to be equal to the log with any base that we feel like. So base b of x over log base b of a. So in this particular case, the natural log is going to be kind of the easiest one to work with because, again, we already know how all this stuff works in the first place. We've probably already done, a number of you calculus type people have already done the natural log of x. Of course, that's easy enough. So if we want to do derivative with respect to x of log base a of x, this is going to be the same as the derivative of natural log of x over natural log of a. We already know that 1 over natural log of a is a constant, so you could just take that out. And then it's multiplied by the derivative of natural log of x, which everybody, of course, knows it's just 1 over x. So this is going to be 1 over natural log of a multiplied by 1 over x. And so naturally we get 1 over x natural log a. So ddx of log base a of x and there we go. So this is one way to do it if you're not really sure about how we get the natural log of x's derivative in the first place. Then we can do, all right, well, 1a, how do we know what the derivative of the natural log of x is? In this case, we say, all right, let's take the limit as h approaches 0 of, here we go, natural log of x plus h minus natural log of x, something like that, all over h. So we use our definition of derivative. I should probably cordon that off in a different color or something, but whatever, it's fine. Okay, and then my head's in the way, so... Nope. So in order to do this, we'd have to use the definition of our logarithms. So in this particular case, we have the limit as h goes to 0 of. 1 over h can just come out, because we have, again, the h in the denominator, and then we're multiplying by the quantity. In this case, we don't even need that. That's fine. We're doing the natural log of the quantity. In this particular case, when you subtract your logarithms, we're going to take their arguments, and then we're going to put them in quotient. So x plus h over x. All right, and this is a really good introduction into how exactly this works, because right here we've got something really cool. So we have the limit as h goes to 0 of, now in this particular case, we've got two things at work here. One is that we've got a 1 over h as our multiplier on the outside, and we've got this whole argument on here on the inside. This is a logarithm. We have a multiplication on the outside. It can be used as an exponent on the inside. So here we take the natural log of x plus h divided by x. We can also divide x into each of the parts, and so that becomes 1 plus h over x raised to the 1 over h. Now, these are not particularly useful things at this exact moment. However, you'll notice that as h goes to 0, 1 over h becomes a very, very large number. So 1 over h, as we get h being 1/10,000th, 1 over h is going to be 10,000. 1 over a million is, or 1 over a 1/1,000,000th is going to be 1 million, etc. So as h goes to 0, 1 over h becomes very, very large. So in this particular case, we say, okay, our limit as h goes to 0 is going to allow 1 over h to become big. So let's just real quick redefine and say let h equal, you know what, let's go the other way. Let 1 over h be equal to n. So in this particular case, we get the limit as, now h, then, if we have this inverse relationship, is going to be 1 over n goes to 0, or we could say that n is going to go to infinity because of this. Doesn't matter which one we use. I prefer infinity. We'll do that on the next line. Okay, so then we get the natural log of 1 plus. Now, in this particular case, we're going to do the same thing. And just out of convenience, you'll understand why. We're going to essentially change positions of the x and the h from the previous line. So what we're going to do is we're going to say, okay, h on the top now becomes 1 over n on the top. There we go. Yeah, we're fine. And x on the bottom is going to become 1 over x. Let's even that up a bit. So we go like this, and we say that this is going to be 1 over n times 1 over x. Okay? And then raised to, this is going to be, again, 1 over h, just becomes n. Okay, now what is that? My head's in the way again. So then what is this? Well, this is the limit as n goes to infinity of the natural log. Or, since there is no n in our natural log itself, not like, you know, not a term n, there's a letter, but that doesn't count. We can actually let this limit slide into the natural log. And we could just take the natural log of the limit as n goes to infinity of 1 plus. Now in this particular case, I'm going to do something out of convenience. I'm going to multiply these things together. But here, I'm going to just let the n take the bottom. And then I'm going to take the 1 over x and put it up top. This, again, it feels really weird. Why are you doing this? However, there is a reason. We'll get to it in just a sec. All raised to the nth power. So, there's a really cool reason why we do this. And that is that we've just had the definition right here. The definition of e to the r is equal to the limit as n goes to infinity of, and let's move over just a little bit here because we need that space. My finger's dragging. I think I need a new glove. I might be able to spring a few pounds for it. Work expense, yes. 1 plus r over n raised to the n. So if e to the r is equal to the limit as n goes to infinity of 1 plus r over n, all raised to the n, what that's going to mean is that in our original, or what we've got going on over here, yeah, it'll work, is that we have the natural log of e raised to the this thing, whatever's in the numerator of this particular fraction. So this is 1 over x. Love it. Right, all the n's get absorbed as part of the definition of e to the r, and so now we've just got the natural log of e to the 1 over x, which means that we just have 1 over x, because the natural log and the e exponent are inverse operations of each other. So taking the natural log of e is saying, what exponent on a base of e do we need to get e to the 1 over x? Well, okay, well, obviously, it's just 1 over x. Right? The natural log is just a question. The question it's asking is, what exponent do we need on this particular base to get us this particular thing? And in this particular case, everything is nice and aligning. Everything has the same base. We don't have any problems. It's beautiful, right? So this is going to be what we get for the derivative of the natural log of x. So makes it really nice, works out perfectly, no problems whatsoever. Okay, so in most of our life, that's not quite how things work. We're not going to get everything to work out so nicely as before. So we do change a base, we can get all that to work exactly the way that we would want it to happen. But again, life is not perfect. Ah well. C'est la vie. C'est la guerre. So, second way to do this is we say, okay, look, we need to take the derivative with respect to x of the log with base a of x. Now let's say we can't fall back on the change of base, or maybe you don't remember what the change of base formula is. That's perfectly fine. Here, what we can do is say, all right, well, we're just going to take the same limit definition as h goes to 0 of f of x plus h, so log base a of x plus h, minus log base a of x. Okay, there we go. Can't get the final parenthesis in there. It's fine. All divided by h. Goodness. Okay. So then what we do is we say, well, just like the other one, the log rules haven't changed just because the base has changed. So the subtraction of two logarithms, I've said before in this channel, and I'll say it many, many more times, logarithms are exponents. So here what we've got is that we've got the subtraction of exponents. So in order to subtract exponents with same bases, you're going to take their exponential terms and divide them. Sorry, that way. Right? This minus this ends up like that on the inside of the log. We can also prove this any other time that we want to. So that's easy enough. Okay, so we take the limit as h approaches 0 of the log with base a of, oops, that's fine. We do the same thing with 1 over h out front. Doesn't change anything. And then we multiply by the log base a of x plus h over x. It's a lot of parentheses, but it's all right. Okay, same deal as before. Limit h approaches 0 of, here we take the 1 over h, make it the exponent on the inside of the log. So log base a of x plus 8. We can do the same thing with the inside as well. Do x plus h divided by x, individually divide them. We get 1 plus h over x. This stuff raised to the 1 over h. And then we do the same thing that we did before. Our limit as h goes to 0 is going to go to the inside of the log. So log base a of limit h goes to 0 of 1 plus, here we can do this now, it doesn't matter when we do it exactly, 1 over x divided by 1 over h. Again, we did all the same stuff before. All raised to the 1 over h. This is then equal to the log with base a of, and again, we say, well, we can let 1 over h be instead just n. So then we've got the limit as h goes to 0. Of, and this is the same definition, 1 plus 1 over x over n, oops, raised to the n. I forgot to remove that 1 over, that h, and 0. And instead make it as n goes to infinity, right? It has the inverse relationship with h, n and h are inversely proportional. So we're going to say that that is the exact same definition that we had before for e to the r. In this case, r is 1 over x, just the same as it was before. This is equal to the log with base a of e to the 1 over x. All right, our 1 over x is going to come out since it's an exponent. Multiply by the... Did I screw that up? Hang on. No, we're good. If I did screw it up, don't worry about it. We'll fix it in post. No, we'll fix it in a minute. Okay, so this is 1 over x times the log base a of e. Oh, right, yeah, this is log base a of e. So you can actually just leave it right here. Most people would be perfectly happy to accept that. But if we're going to say, well, log base a is kind of difficult to do on your calculator sometimes. If you have a TI calculator, hashtag not sponsored, it's easy enough just to say, well, I want to do a log with a particular base. And you go into the math menu all the way at the bottom of whatever menu you're on. I think it's just the number submenu. If you go all the way to the bottom, I recommend pressing up, and it just cycles all the way down. You get log base. And if you have a new TI calculator, meaning like in the past 10 to 15 years, it has this built in. If you have one that's older, you actually have to know the change base formula. Or if you have a like scientific calculator, if you just take your phone and then turn it sideways on the calculator screen, you can have either a log base 10 or a natural log, and usually that's it. But if you don't remember, right, you can always say, okay, right, this is going to be log base A of E is going to be any base you want, which of course we're going to choose log base E, natural log, because this makes the easiest one possible. This, we're going to say this is going to now be 1 over x times log, natural log of E. What exponent on a base of E gets me E? It's 1 over natural log A. Right, which is then going to be 1 over x natural log A. And that's exactly what we found before. Right, and we can decide if we want to leave it as this, if we want to have this be 1 over x times log base B of E divided by a log, base B of A, right? It doesn't matter what base you're using here. So if you particularly like base 4, go for it. Have fun. I'm not going to care that much. Whatever you feel like. So anyway, yeah, I submitted this on Twitter for the person who was questioning, and she was just like, "Ah, great, thanks." You know, 1,000 other people had probably responded by the time I got to it, but I didn't see a like full proof of how it works from like the definition of derivative. And so I just decided, all right, that's going to be my niche. And I went and got my, you know, spiral ring notebook while we were on vacation. Kids are off playing somewhere. I'm just like, I'm going to knock this out. And about 5 minutes, I had, you know, this, I don't know, what, 6-line proof? Something like that. Yeah, 1, 2, 3, 4, 5, 6. Good enough. Maybe 7. So it's quick enough to knock out. It's fairly easy to figure out just, you know, how do derivatives work. Let's start from our base knowledge. So what are derivatives, right? Derivatives are this, or how do you find derivatives? We use the definition of derivative, right? Well, it goes the other way, really. But we're saying that the derivative with respect to x of a function f of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, why does that work? Well, that's going to be the same as if we took the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by x plus delta x minus x. All right, where does that come from? Okay. We got a curve. This looks suspiciously like a root slash log function. It can be pretty much anything you want. It doesn't matter. What we do is we say, okay, pick a point. This is going to be your x comma f of x. Don't care what it is. It could be a curvy function that jumps all over the place. Your choice. And we're going to pick another point out here, which is going to be x plus delta x, comma, f of x plus delta x. Again, calculus review for anybody who doesn't remember. And then we're going to draw a line that goes between them. Nice. Didn't even have to resize it. Nice. Hey, Sensation, how's it going? Saw you pop on earlier. I was, I think, making dinner at the time. Let's see. Anyway, this is a secant. Yeah. VB.net with a passion. I'm sorry. I did have to play with Visual Basic for about 6 months at my job before, working at the community college. It was not .NET, I will say. It was just macros, which was bad enough. Yeah, our department was trying to put data into a database, and 1998, wow. That's about right. We were trying to put information into a database that was providers of medical services. We were trying to get all of their information put into the system using this Visual Basic macro system. And it was all, its own little Visual Basic window that had been gussied up by whatever UI developer, probably in 1998. Not much had changed. And they were, the group I was working with were radiologists in Maricopa County, Arizona. Very specific, very niche. And then eventually I moved out to nationwide, all of the radiologists in America, the United States. And they had this interesting, they have this really weird teleradiology system where, like, if you have a license anywhere in the United States, you can usually get a reciprocity deal with any other state in the union. And they'll be like, yeah, sure, you have the ability to read radiologist, to read images from anywhere in the country. Like, you had to specifically register with each individual state, but it was pretty much just a reciprocity deal. Like, yeah, no problem, we got it. So they'll ship all of their images in a particular company to Maricopa County, and then those radiologists read them and then ship them back. Fortunately, it was all digital, so it was nice and fast. But the way that it worked was I had to go into each individual provider's record, find out who they worked for, go to the list of companies that they worked for, some of which are different DBAs, doing business as, and copy down all of their individual numbers, and then find out all of their individual tax affiliations. There were sometimes many, because for every single different state that your company reads for, there's a different tax ID number. And then you have to take all of that information and put it on the provider's record. And I went about, 2-3 days worth of this, and I was like, man, fuck this. I don't have time. It was taking me like 2 hours to get one provider done. And I was just like, no, this is stupid. A computer can do this. So I got the Visual Basic macro, and I called my buddy Dave over. I was like, Dave, you gotta help me with this, because, like, I don't know Visual Basic, but let me know. And so Dave's like, all right. So this is kind of the way Visual Basic works. And I was like, okay, so, like, is this the structure? And I build out a program. He's like, yeah, that's fine. Like, there's some nuance here, but you know what? You pretty much got it. So I spent like 2 hours with him getting primed. I spent about 40 hours, the entire next week working out exactly how this was going to work and yelling in frustration at it and calling him back over for, a minute, being like, no, that's not the way syntax works. Fix this. And then at the end of the week, I spent pretty much like it was only a 6-hour day. All right, so it was only 24 hours of frustrating yelling at the computer and fixing things, and then about 6 hours of making it work and tweaking little things. I went to my boss and I said, all right, look, my numbers are kind of low for this week, but I promise you they're going to be like spiked next week. And she's like, okay. So I spend the entire day Monday running it, doing nothing else but just running it. And on Tuesday morning, she comes up, slams her stack of papers down on the table, and she's like, what did you do? I'm just sitting there laughing. I'm like, yep, okay, let me show you. So she thought that I was just like manipulating the system to make it, basically like add and subtract. I don't know what she thought I was doing, but I was like, no, let me show you. So I pull it up and I show her, all right, I click this, and now it goes in and it reads the individual, it reads the provider's record and copies all of the places they work, puts that into an array. Then it goes into the first place and it copies into a secondary array all of the tax affiliations. And then it goes back to the provider's record and writes them all. Then it goes back into the next company they work for. So number 2 on this list, copies all their tax affiliations, writes them into the provider's file. Goes to the third one, and et cetera, et cetera. It goes all the way through everything. There were only like some minor fixes that needed to be done. Occasionally it would stall because it's expecting this one little field to be FS, and instead it's actually supposed to be FN because it's belonging to like this very, again, niche problem. So showed her everything, how it all worked, and she was just like, you could do that? I'm like, yes. This is a very simple macro. The biggest problem I had was occasionally you'd need to program in a wait time so that it would populate the next screen before you execute the next code. It was really frustrating, but whatever, fine. So I got all that stuff. Oh, yes. Now, granted, it was only a $500 bonus, but that was $500 for 20 hours worth of work. So, like, yeah, on top of my regular, hourly wage or whatever. Yes. So, 20-ish dollars an hour extra. I wasn't really complaining that much, even though this technically was getting our stalled project back on track for like there were 4 people working on this before I got to it, and then they were all one at a time taken off to work on something else that was actually more pressing, and they were like, whenever you have time, figure this out. And I was like, great. But yeah, so it was a stalled project that they were just like practically giving up on. And I got it back on track single-handedly with, literally 20 hours worth of work. So was it 500? I think it was 500. I suddenly had a thought, like maybe it was 1,500, but no, it was probably 500. Yeah, the company's not going to pay off like a huge amount, but but I was like, I went to Dave, the guy who, reminded me how Visual Basic works. I was like, hey man, I'm gonna buy you something. So ended up buying him like a game from the game store, because we were also part of he was also hosting a lot of game days and stuff like that with his friends. So Here's my appreciation. Interesting. That could be a number of different things. Yep. Yeah, so I've kind of messed around with channel moderation settings. It could be that I put it to, like, you know, family friendly or something like that, which, whatever, it's fine. Yeah, I'm sure that the CEO knew exactly how many hours I saved them. But oh well. And it was like, this was a job that I got hired at, I want to say 36,000, which you're only supposed to, like, need a master's degree for it. Or sorry, need a bachelor's degree for it, which was about on track for how much I was going to get paid pretty much anywhere else. So I'm like, whatever. And then I had to prorate it to 30 hours a week instead of 40 because I was also working at the community college as an adjunct. I was doing either 1 or 2 classes a semester just to get experience, to try and get my foot in the door, to have everybody recognize, like, hey, I should be on your staff. And it was... yeah, so we also have an associate's, which is a 2-year degree. That's what we would give out at the community college. And it's not trade school because it is academic. I don't know what the equivalence is. But, yeah, is A-level like the equivalent of a 2-year experience? Give or take. I need to do my research on UK education, obviously. 2 years to get into uni. Okay. And then uni is another 4? Or if you have A levels, do you get like a leg up? Or more, depending. Okay. Yeah, so it seems like A levels are kind of your masters in 5. Yeah, okay. So we usually do masters in 5 or 6, depending on what program you're in. So, like, my education program would have been 5. I could get a 1-year master's if I did all of my classes concurrently with an internship in a local high school. So it would have been like absolute murder to do it, but I could have done it. Instead, as it was, I did 4 for bachelor's, and then I took 2.5 for my master's because I was only doing 1 or 2 classes every semester in the opposite role as me teaching classes. So it was either 1 or 2, but in the opposite amount. And it all depended on when my classes were offered for the masters, because, you know, there were certain ones that I definitely wanted to take, and other ones I definitely did not want to take. The stochastic processes and master's level statistics I did not want to take. I took 1 master's level statistics, which was required for everybody, which was calculus-based statistics, which was fine, except, and I've said this before, the teacher had this habit of writing on the chalkboard and then turning around with his eyes closed, looking at the class, and then looking at the top corner of the room and speaking, and then turning back around and writing stuff on the board, turning back around to the class with his eyes closed, looking up at the corner of the room and opening his eyes. And I'm just like, oh God, this is going to kill me. Like, he's got his thing, and it works for him, but at the same time, like, It's a habit, and I've now noticed it. Uh, I don't know if it was anxiety or if it's like a tick or just some odd. I don't want to, obviously I don't want to like diagnose, but like maybe autism spectrum disorder, maybe like it's just the thing that he does. But yeah, it was like, okay, like this is your thing. Maybe it's anxiety, maybe it's just a thing that you're doing. But yeah, it was like, I've now noticed it, and it was hard to not notice. Then like I'd ask a question and he'd look directly at me. So I mean, at least that was the case. But it was also like if somebody asks a question, he would also kind of look at them with like a disbelieving look, like you're interrupting me. I have a script. So maybe I'd lean more toward anxiety for that. But yeah, social anxiety, social cues, whatever. This was also a program where every teacher was a professional at the Johns Hopkins Applied Physics Lab. And so, like, every person who was a teacher also worked there, and so they're not actually trained educators. They're instructors who can, in fact, instruct everybody at how to do things. But I'd say probably all of them, almost all of them, had like zero training in how to teach classes. And so I'm just like, oh. Me, the person who had a so predominantly there is an entire wing of Johns Hopkins that is devoted to medical, and like they do the campus that's in Baltimore. So the campus that is like the main campus in Baltimore City is a medical university. It's not exclusively medical. It's always had a good mix, mostly undergrad, but their graduate program in medicine is extremely good. Their graduate program in law, I think, is fairly well known. Their like STEM stuff is very good, but like if you're doing graduate work in mathematics, especially, you want to go to Chicago. Like University of Chicago is the place to be. But Hopkins is very well known. I was at the Applied Physics Lab in Laurel, Maryland, which is not very well known. but I still went there and yes, MD or medical doctor if you want to go there too. But I still went there because the program was convenient. It was close to our house. It was, I don't know, maybe like a 20-minute drive or something like that. So sure, why not? From my college, it was like a 10 to 15-minute drive. It was very convenient. That probably just gave it away for somebody. But yeah, I kind of liked it. I was a little bit miffed at the fact that our instructors were not educators in the sense that they don't necessarily know how to teach, apart from what they've just kind of gleaned. Do radii. What? Oh, yeah. Get a map. I got you. So yeah. So, and let me tell you, 15 minutes is very different over there compared to here. Oh man. It said we were 40 minutes away from our destination and had 15 miles to go. I was like, are you kidding me? But no, that made sense when we actually got on the road. Yeah, we're often we're anywhere in the United States. It's like 15 minutes. All right, you got to go about 15 miles. Somewhere between 10 and 15 miles. Here it was like, you got 15 miles to go? Awesome, 40 minutes. I'm like, ah. Oh. But I mean, it was right because we had the average speed along that entire stretch was probably about 30 miles an hour, depending on, a little bit higher, maybe 40. Yeah, exactly. My spouse looked up when when the next train was going to be, because we had actually stopped at a train station, because I was like, I don't effing know where to go. We want food and we want bathrooms. Like, I don't know. Where do we want to be? Like, where do we want to go? Fine, I don't know, train station. Let's, because that was the most easily recognizable place. And, my kid's like, you've ignored me because I had to go to the bathroom so bad. And I'm like, I didn't realize you had to go to the bathroom so bad because you just said, like, hey, next time we stop. And I was like, I don't know, we're going to pull off here and find food. Sure. 20 minutes later, pull into the parking lot, and she's like, ah. But anyway, yeah, we sat down for lunch, and spouse takes out the phone and looks up, like, how long would it take for me to get from here, literally the train, which leaves in 5 minutes, which she would have never made, to be clear. She would never have made it in time. How long would it take me to get from this train, or using this train to get from here to home, which is, we're within a few minutes walk-ish of a train station. So, how long would it take? She looked it up. It was like, you guys, it's going to take about 45 minutes to get there by car, and it would take me about 40 minutes to get home, like, including train and walking. So it was like, roughly the same amount of time, but probably the train was faster. Then our kid looks at her and is like, yeah, but you wouldn't have lunch. She's like, well, there's the plan. It's completely scuppered. Yep, 100%. All right, I'm going to take a quick break here, hit the cycle some water. And actually enter my who's it? Trivia League answers and whatever. So we'll take a 3-minute break. We'll come back and we'll talk more about calculus. And if anybody has any questions, feel free to drop them in chat. I will be right back. So those of you who don't know me, I am Obi-Wan Pez. This is N Simplex Pachenko. We do math here. So be back in a few. Alrighty, and we're back. Hope everybody got a nice little stretch in or something. At any rate, hydrate everybody. And again, if anybody has any questions, feel free to drop them in chat. So I forgot the Roll the Dice app was a good one for Twitch. Thanks for reminding me about that. Yeah, still definitely didn't submit. Let's see. One question is about world politics. Somewhere between world history and current events. Oof. This guy's #1 category is current events, but world history is very low. Put a score for that one. Games and sport, he'll probably know chess pretty well. Geography, pretty good. Business and econ, also pretty good. Oh. Literature, fairly crap, just like mine. And sport, pretty close to the top. Yeah, we'll go like that. Alright, second person. Math, science, and games and sport are at the top, so I'm going to go with 0 for chess again. Business econ's pretty high. There's a significant fall off for literature. So that's good, probably. Geography's pretty down there as well. We'll go like this. We'll see how it goes, because quite frankly, I'm not doing terribly well in this trivia league anyway. So okay. Yep. Okay. Yeah. All right. Whatever. Of the 6 questions, I got 2. Ouch. But we'll see how everybody else did and whether they got screwed over as well. All right. Apologies. Okay, so 4 hour. Yeah, and obviously Sensation asked me any other questions you want about the other stuff we were talking about, or if we can continue my story because I don't even remember where I left off. Anyway, much of calculus is built off the idea that instead of doing a secant line, what we want to do is to build a tangent line at a particular point. So that we want that tangent line. All right, so that secant line is going to take the entire inside here and say that the slope of that secant line is going to be given by this slope formula. It's just a slightly different way of writing it. It's f of x2 minus f of x1 all over x2 minus x1. That's my mother. Nope. Okay. Okay, so in order to find the slope of the secant line, we subtract our y values, and then we subtract our x values, put them in ratio with one another, and that's how we get it. In order to find the slope of a tangent line, we do the same thing, but then we say, let that delta x, the difference between the 2 points, go to 0. So eventually we're, in theory, overlapping them and saying, hey, you know, close enough. Once we get really, really, really close, what happens? Anybody who's not sure about limits, let me know, because it's fairly easy to figure out once we actually talk about it a little bit. But okay, cool. Oh, nice. For anybody else, boop. Sensation Black is one of our Twitch friends who often comes by and says hi and checks out a lot of our other math content, and, you know, the rest of our content too. So go ahead and give them a follow as well. We also have currently live Enigma. Hey. We have Ian Stuckey. And we have Dawn Does Math. Dawn was the one we gave a shout out to earlier, whose live message was 95% of people can't unscramble this, and gave us E pins. Obviously the answer is spine. Get your mind out of the gutter. And Ian Stuckey is another of our math chads who, for anybody who wants those, who are part of our unofficial stream team. We were all math educators, and we came together in about November. I found, really, it was the other way around. Zach and Penn found me, and I was just like, all right, cool. And then they were like, no, we do this too. I was like, whoa, wait a second. I started paying a little bit more attention to the math category. And also they use sometimes science and tech. So, gets to be pretty fun. Let's see, what other stuff do I want to talk about tonight? So, while we're on a Calc 1 kick, we can also talk about some of the rules that exist. Oftentimes on this channel, we will use the generic derivative operator, so D, rather than ddx. And there isn't much of a reason why I do it particularly. However, there is one important difference, excuse me, and that is when we take the derivative of a particular function, we do get, f prime of x, which is the derivative of x, but then we need to do the chain rule as well and take the derivative of the inside. The derivative of x is dx. So this is one thing that I recommend, especially if you are going to be working at all in the domain of differential equations. So differential equations itself is just a field that really loves having differentials like dx attached to particular functions. Now the difference between this and ddx is really, there isn't one, but typically if you're doing ddx of f of x, then you're going to get, we're going to get f prime of x times, now we take the derivative of the inside, it's ddx of x. And, well, ddx of x is just 1. Or if you want, we can do dx dx, which is f prime of x times 1. So it's just f prime of x. We do like cramming stuff in all the way on the corner of the page on this channel, so. So in this way we can say, all right, if we just want to take the derivative of a particular setup, so for instance, f of x plus g of x, oftentimes what we get is the limit as h goes to 0, same deal as before. Here we get f of x plus h plus g of x plus h. Never gonna viv you up. Hey, how's it going? My name is Obi-Wan Pez. This is N Simplex Pachinko. We're having, oops. And there we go. Our first mistake, no. Used to be. So, yep. So, yeah, I go by the handle Obi-Wan Pez because did I really not have it nearby? That is ridiculous. One sec. I think it's back here. The other possibility is that it is in my stuff. The good news is that my stuff is coming to this house in 6 days. So, well, okay, 6.5. So, I swear it's here. At any rate. So I will finally have my desk, be able to sit at it, put my feet up, instead of sitting on the floor and getting cramp every single day. Yeah, I must have left it somewhere else. On the plus side, I do have a calculator. That's weird. Yeah. I'm pretty sure I brought it with me on my person, but I can't find it, so, oh well. The reason that I'm pretty sure that it's around the reason that I'm pretty sure that my Pez dispenser is around is because I brought these with me. So, like, if I brought these with me, I'm pretty sure I brought the Pez dispenser with me. Yeah, this is my Einstein. I used to have this on my desk at work in a corporate office. And this is the Einstein action figure. He has a piece of chalk, and his arm is fully articulated, can bend at the elbow and the shoulder. His hair is, in fact, nicely frizzed out, and I would oftentimes have him up on my desk and have a little post-it note right next to him that said something, because one of my other coworkers had like a John Cena doll, which also had a little like erg. So I was like, well, let's bring some intelligence to this. And it would usually be like an Einstein quote or a Douglas Adams quote or something like that. Not me being pretentious, I promise. And yeah, our Vault 101 lock picker. Because that's the other thing. I definitely have that. But I can't see them where I'm sitting. I have I am an accomplished, although not expert, lock picker. So I can actually pick locks. If you do it in the UK, though, where I've just moved, you can be taken into custody for coming equipped, meaning that you are intending on doing a robbery, or intending on doing a burglary. So I have decided to leave them at home. Yep, I saw the Fallout show recently too. It was one of my friends from high school was in it. So it is really awesome. He was also in oh yeah, I mean, I'm not gonna I'm not the criminal. But anyway, yeah. I mean, there's plenty to steal. You just don't do it because, like, you actually know your neighbors. So this particular person was in Fallout. He was also in Reservation. Yeah, Reservation Dogs. If you haven't seen Reservation Dogs, it's really good. He was also in uh, a show called ugh, Selfie, starring John Cho and Karen Gillan. But yeah, it was really amazing. Like I got to see him on TV, and I was like, dude, I know that guy. And then he was in Reservation Dogs. I'm like, dude, I know that guy, and he shows up more often. I mean, he had kind of a recurring part in Selfie, but it was also kind of like it was very small. Every time he'd come in, it was only like one or two times per episode, and like a line, and then go. But it was very much like that is his personality. Definitely, 100%. I know exactly who that is, and I was just like rolling. So I'm like, that he has not changed one. I mean, you know, got older, grew up and stuff, and whatever. But at the same time, it was like that guy right there, 100%. I could see that personality shine through. He was also in Jurassic World as like a ride operator, and I didn't actually see Jurassic World, but I should probably do that at some point. Um, and then yeah, Reservation Dogs came around. I was like, dude, he's in this, and again, definitely that personality shining through. And he was in Fallout, and I was like, okay, you're only in it for one episode, but let me tell you, it was just hilarious. Loved it. And if you've watched the entire series, you know who he is. He was one of the stoners. Right. Anyway. um. So yeah, to answer your earlier question, I am or was a professor at a 2-year community college in the United States. My family has since uprooted and moved to the United Kingdom. We're living in, broadly speaking, Yorkshire, and it's a series of I don't even know how many counties, but in the north-ish part of the United Kingdom, or north-ish part of England. Um, we're, roughly, or Yorkshire itself is roughly speaking about halfway between Edinburgh in Scotland and London in the south of England. So no problem. My spouse got a job. Well, I mean, my spouse has had a job um, in the United States for the last basically 20 years, and an opportunity came up here in England, and we were looking at, like, well, do we want to do this because it's gonna like really uproot the family? Like the kids are gonna have to change out schools and all this other stuff. And then we looked into the financials, and they're paying for the kids' schooling. They're paying for our rent and utilities, or like, there's a stipend for it. And I have a work visa if I want it. So, like, yes, please. So I have the ability to work in the UK, and basically any money I make whatsoever is just going straight to the bank. So at the moment, I'm not really doing anything. I am trying to build my presence on Twitch and try and get some of my stuff ported over to YouTube, and finally script out some videos so that I can do math education on both Twitch and YouTube. So it's going to be cool. We'll see how it goes. I don't know exactly what I'm doing, but nobody does. So yeah, it's a lot of benefits, and like, you know, basically, I mean, because we don't have to pay for housing, that's a significant chunk of like all that stuff. Math and animation. Yeah. There was a point where I was like, I really need to do Grant Sanderson's challenge, which was the 3 blue 1 brown channel. He made a challenge that was like, hey, any math educators out there, you know, you can have basically free access to like my animation system. I think that was the deal. And I want you all to like make something that is going to explain a particular topic. Just do the best you can with it. And it was a contest, so it was like, you know, the best one is gonna be like get highlighted by him on his gigantic channel. At the time I was working at the community college and like didn't have any real time to put into it. I wanted to do it, but like it's kind of a lot of work, and again, I was not super able to keep up with trying to do that and also make sure that I kept my job. You know, things go like that. Almost. There. So right now we're working on some calculus stuff. If anybody does have any questions, let me know. Ah, that's cool. I mean, I really look up to him as a educator, generally speaking. His math stuff is pretty solid, so like... Oh, right. And if we're doing generic derivatives, this is going to end up multiplying by our delta x. Technically, this is on the inside of that parenthesis. Okay, and then all these. When we take the limit as h goes to 0, our delta x becomes dx. Now we can make this f prime at x plus g prime at x. Times dx. Right, and that's our generic derivative for f of x plus g of x. So yeah, Grant seems like somebody to look up to. Yeah, UK is really good so far. It's only been about a month since we actually like moved in. So, oh, wait a minute. Hang on. No. It's been like a month and a half now. We just spent a week, or like half a week in Wales, and it's absolutely gorgeous. We went on a dolphin cruise and saw some dolphins off the Welsh coast. The guys who were running the tour were like, yeah, we spent like our entire hour on this last cruise seeing absolutely nothing except, you know, there's some birds on the water and up on the cliff sides. And it's really cool because there's like 3 different kinds of birds, and you don't often see all 3 of them living together. But like this is like the one part of the Welsh coast where you typically see it. This was New Quay in Wales, and the tour operators going on about some cool stuff about what, you know, things you see like that. And he said it wasn't until we turned around and were just about to head back that a couple of dolphins started splashing around, and he's like, but we got to go back. So he was like, we just saw them at the tail end of last one, so hopefully we'll still see them. And so we got like all the way out to where like there's a little inlet where all of the cliff birds are nesting, and they're like, you know, this is where we saw them, but I don't know if we're gonna see them. And then like we see, you know, little dorsal fin followed by the fluke, which granted the dolphins don't like show off the fluke like whales do, but you could definitely see the rear fin. It was like, yay, we got them. So we got a few pictures, we got a couple of videos, and then like we started getting a bit closer. And I mean, these are wild dolphins, so they are not gonna approach the ship or anything like that unless they're hoping for food, which they don't. Like this tour does not do that, right? You're not gonna feed the wildlife and make them dependent on humans. It's awful. So he the captain pulled the boat around and then, you know, quieted down the engine a little bit, and we saw that it was one big one and one small one. We're like, oh, that's so cool. It's a mother teaching her baby how to, you know, come up for air, or when to come up for air, how often, that sort of thing, and like how to properly do it, and all that. So we got to see a little educational moment. It was great. And our kids love it. Their ages are roughly. We also kind of love this fact. It's 7 and 11, so like our younger one was like, we've got to take a picture by a 7-Eleven because those are our ages. All right. Yep. And of course, we don't have a 7-Eleven in the UK, so it was like the day before we got on a plane. We were like, okay, we have to do it today because literally this is it. Yep. And then by the time we get back to America, right, I mean, even if we were to go back on vacation or anything, by the time we go back, like 99% likely they're gonna, at least one of them is gonna be a year older. So, or, you know, number wise is gonna be a year older. So yeah, we saw Wales. We're gonna go up to Scotland later on. Oh, it just turned 1. That's awesome. and everybody's gonna go, oh, it's such a great age. Yep, ours, yeah, it's so messy, but at the same time, it's so great to just watch. And my spouse and I both took neural networks as one of our classes for master's degree, and so like we had been our instructor had taught us a bunch of like, here's how the brain works, and to watch that like actively happening in our child, both of them, um, was just like absolutely mind blowing. Uh, and at the same time, just really cool. And like, growing up, our parents had always told us, oh yeah, your first word was like mama and dada and all this other stuff, and our kid, our older one, hits about like 10 months, I don't know, something like that, and she goes up, and we're like, excuse me? And she's like, up. And we're like, how is that even what? You want to come up? And she was like, and picked her up and gets that look on her face like triumph. We're like, okay, well, that's your first word, all right. And we go camping some number of years later when our first one, or when our second one is, God, how old was he? 8, basically 6. So yeah, he was 10 months old, and he points at a dog and goes, dog. Like that, and I'm like, well, no, you can't. You. What is it with our kids and their glottal sounds? Like the. At first, it was more of a duh sort of, but it was very clear. He pointed at a dog and said "duh," and we're like, "Are you joking?" Yeah, also true. So our older one, whose first word was up, has always been like super empathetic, and there's just a whole bunch of like, she's really smart, we can tell, and she is almost always trying to like be, she is almost always trying to be like the to be like the psychologist who's like trying to work out everybody's problems, not in necessarily like a very personal sense, but like, oh, well, it must be really hard. Let's talk about that, and like asking and we're just looking at each other like, is she seriously counseling people at age 6? And like, she knows just intuitively all of the like stuff that we'd learned through speaking with like our psychologist friends and stuff like that. And yeah, we're just like, that is, how is this even possible? And then our younger one gets to kindergarten and starts learning some basic arithmetic, right? And we're just asking him a couple of questions about like, how did you get that? Like, how does your thought process work? And he like can't explain how he thinks, but you ask him a simple arithmetic question with just addition, subtraction, or well, now multiplication, division, and he'll just like know the answer. And we're just like, what the hell, man? This was another thing that I wanted to get into, was trying to work out how the American Common Core mathematics system works. That'll work. So there's like multiple different ways to do this, right? What they've been trained to do is more or less to do what probably any of us here would, generally speaking, do, which is to decompose the number. Now, we don't do it longhand. Right. Now, again, we don't do it longhand. But they're taught initially that you're supposed to decompose the numbers so that here we have, okay, this is going to be 8,000 plus 700 plus 800 is going to be, and the way they do this one here is they say, well, 800 is going to be 300 and 500 separately. So that these get you the nice 1,000, and then we have the 500 left over. So it makes it much easier for them to do the math quickly at an early age. Again, when they get older, it's not so bad. It's just like, okay, yeah, I got it. Again, 10 from the 40 to make that 100. So 130 plus 10. And then they say, okay, well, same thing. This is going to be 1,000 plus 500. Sure, they know already. They know already how to move this stuff. By the time they get to like 3rd grade, they're already just doing this stuff in their head, like instantaneously. So 9,640. Now, I would argue that this takes about the same amount of time for us to do it as for them. Hey, Nep, how's it going? My name is Obi-Wan Pez. This is N Simplex Pachinko. Let me know if you want to be known by any other name. The British system, the way that they're learning it now, is almost, but technically legally distinct from how we learned it back in the day, which again, our stuff was all this carrying, quite frankly, nonsense that we did. So, yeah, 10. I shouldn't confuse this, right? Because this is not the British system. The way that they're going to do it is they're going to say, okay, 8 plus 2 is going to be 10, like this. And the carries go under instead of on top. My spouse and I both looked at this and went, huh. Yeah, that makes way more sense. The 9 plus 4 is going to get us 13, which again, we just carry it through. And it's essentially, we're doing this right here, right? All right, then 7 plus 8 is going to get us 15, carry again, and then 3 plus 5 is 8. And then we go like that. This one's a 0 because it didn't carry anything. And then we just add straight down 4, 6, and 9. Oh, look at that, 9,640, same thing as they got over there. Now, the British system is also related a little bit to the method by which or the method which was encoded in the Hindu Vedas. And I'm not kidding. Yeah, Nep, if you have any questions about mathematics or me personally, let me know. I can drop it right in chat, and otherwise we'll talk about all sorts of stuff. Right now it's a little bit of mathematics type stuff. It kind of depends on how you look at it. So in terms of like, there are many different rules. Some people can get bothered by that, and it can hurt a little bit. I found it easier because from my mind, it was like starting over. Yeah. So I think the more important part, rather than necessarily trigonometry itself, is the pre-calculus function analysis portion. Well, you just keep coming back, Nep, and we'll make it work. So I also have a list of the math chads who are the math educators here on Twitch, who are part of our little enclave. I don't know if I want to use that word, but we're an unofficial stream team. Dawn does math, Zach, also known as E to the 2i pi, Penn Center, E.N. Stuckey, Obi, myself, Danny Highway, and Dr. Gold at Actual Education. So we are the... How many people is that now? We are the 7 major math streamers, at least that I know about. There are several others that are out there, but I really haven't spent any time like in their channels and hanging out with them. So I have been streaming on the math channel since 2021, I think, maybe 2022, and like I have not seen a large number of viewers, and as of November, when I contacted Penn Center and Zach, they had actually come into my channel and like hung out a couple of times, and I was like, hey, this is really cool. What do you guys do? And they're like, hey, we also stream math on Twitch. And I was like, wait, what? Like, I've been scouring this channel for months. Are you kidding me? And they're like, oh yeah, we stream under the like science and tech. And so we started talking, and we're like, no, we're gonna take the math tag, and we're gonna stream under the math category. That is where we're gonna live now. So we've been doing a lot more. They also knew Dawn and Danny Highway, and then we found Dr. Gold. Ian Stuckey ended up contacting all of us at some point. And like hung out in Zach's channel, I think. And we're like, hey, we're gonna all do this now. Yeah. Well, it's also like, this is not this is not my usual time. This being 5 hours back, it would be roughly 6 p.m. I was at US East, and so there was very little overlap between me and a lot of the other streamers. I found out they were streaming at very different times. Financial math? Absolutely. Yep. I did financial math as a part of not like super intense stuff, but amortization and compound interest as a part of our 2-year college's like generic like math for whoever needs to take it. Sell your company or retire. Yeah, it's one way to go. Well, I am looking to start my technical LLC slash corporation slash whatever. So if you have any advice, let me know. And we'll be on the major Discord server that we use is actually Penn Center's. So if you go to Penn's Discord channel, his is the one that we like constantly go to. Just trying to hang out and stuff like that. So yeah, you can usually find us, all of us, in there at some point. So I would like to solicit any ideas. I know that being in Britain, it's going to also be very different to being in the United States. So I'm going to seek legal advice on. We got a free legal aid sort of thing going on next week. So I'm going to show up to them. Know your customer base. Focus on customer acquisition. Yeah. And for this, it's going to be a bit different because I'm not like super, right? It's YouTube and Twitch, so it's like a little bit different. But anyway, at some point, I might also branch out into like a slightly different space. So we'll see how it works. But yeah, thank you. Quant firm. Investment lucrative. Yeah. Is it stable? Anyway. Anyway, yes, I'm sure it's fine. Yeah, so the Vedic math actually was encoded into the Hindu Vedas because they knew that one of the most important things for your civilization to do in order to survive is to pass on knowledge. And, what's better than math? So here, what the Hindu Vedas did was they said, okay, we're going to add 8 and 2. And again, this was like in the Hindu text rather than in our Indo-Arabic. So the numbers are slightly different, but honestly, it looks pretty much the same. As they'd say, okay, this is 10. So our 1's place is going to be 0. Our 10's place is going to have an extra 1 added to it. So they'd put it down here as like a subscript. Yeah, the numbers are similar. There's some slight differences, and I'll do at some point. But I was also studying math history as part of my work at the community college, so it was really cool looking into it. Oh, nice. 9 plus 4 is 13, but we get the 1 from over here, so we get a 14. So again, carry the 1. In India, yep. 7 plus 8 is going to be 15, plus the 1 is 16. And 3 plus 5 is 8, plus the 1 is 9. And so there you go, 9,640. Again, same answer, obviously. We always should get the same answer here. But in slightly different ways. As soon as I learned the Vedic math, I was like, I need to start teaching this to my students because, like, the fact that we're only doing one line is super interesting to me. And, like, we were able to get all of this stuff in one line of text. I loved it. Now, the other problem that I have with all of this is that it doesn't really do much for us. So whether it's the Vedic, the British, or the current, former American system, again, 3798 plus 5842. Apologies. So this is. right? We're starting on the right. We're doing, okay, here's 10. This is 10 plus 4 is going to get us 14. Carry again. 7 plus 8 is 15. Plus 1 is 16. Carry again. And then 5 plus 3 is 8. Plus 1 is 9. Right, classic American system. Very similar to the British one. It's just that all the carries are at the top instead of the bottom. And it ends up taking up, you know, roughly the same amount of space plus a little bit at the top as the Vedic one. Yeah, okay, fine. Okay. Now, the American Common Core system is a lot messier, and it takes up a huge amount of space. But again, eventually what you're doing is you're just shortcutting this whole process, and you're ending up using mental math a lot more as you get more experienced. Now, here's another thing that's really interesting about the Common Core system is that if we then say, okay, well, what we want is 3x cubed plus 7x squared plus 9x plus 8 plus, okay, like this number here, plus 5x cubed plus 8x squared plus 4x plus 2. Somebody who's memorized these systems over here, like our British, American, even the Vedic one, like, it doesn't really track. It doesn't really help you do this problem right here. But what's going to happen is that we're constantly reminding the students in this Common Core system that what we're looking at are different units of the numbers, and that's why we broke them up. So it was 3 thousands and 5 thousands. Those units go together. And now, instead, what we've got are 3x cubed. Well, these are different units than 7x squareds. So in this particular system, right, all of the x terms are different units. So we need to bring together the separate units. And so we get 3x cubed plus 5x cubed plus 7x squared plus 8x squared plus 9x plus 4x plus 8 plus 2. And then all at once, right, this is going to become 8x cubed plus 15x squared plus 13x plus 10. And if you look at where we had those exact same numbers up here, trying to melteth my braineth, you are succeedingeth. Yes. I mean, somewhat fair. But, like, again, these numbers are echoed here. And it might not be explicitly obvious at first. Abacus, nice. Yeah, I've wanted to kind of like start teaching my kids how to use the abacus properly. I mean, I still need to learn how to use the abacus properly, but the base and the power are somehow reflections. So sort of. I mean, what we've got here is if x equals 10, we've got 8 times 10 to the third plus 15 times 10 squared plus 13 times 10 to the first plus 10 technically times 10 to the 0. Right? That's just 1. This is 10, so that's 130. This is 1500, and this is 8,000. And wouldn't you know it, we have those exact same numbers up here at this line. So showing algebra students how this works is going to help out to be like, hey, by the way, you've already done this stuff. This was like second grade for you. You know where this connection is. This has a deep connection. Whereas if you show somebody all of this stuff over here, any one of them, it doesn't matter, it has a lot harder of a time, or the students have a lot harder of a time to actually connect these things and say, oh, these belong together. Like, I sort of got it, but I didn't really. None of my teachers really explicitly laid that out ever. I think maybe in Algebra 2 we finally got to like, oh, by the way, this is the same thing because you're doing long division, right? If you're doing long division in Algebra 2, it's real easy and nice to connect the fact that here, this polynomial is very similar to this polynomial over here, is very similar to, just doing some random division. The base and the power are somehow reflections. So, sort of. If I'm understanding you correctly, Sensation, we're saying if you're going 2 to the 6th, what you want here is you're saying that I want to change the base so it's not 2 anymore. So I can let this be 2 to the 2nd parentheses to the 3rd, or 2 to the 3rd parentheses to the 2nd. Because in this particular case, what we're doing is we're saying that if you have any base that's raised to the mth and nth powers, this is going to be b to the m times n. And we can sort of hand wave our proof and say, like, if you need to actually do this out, right, this is going to end up being 2 to the 3rd 3 times. Sorry, 2 to the 2nd 3 times. Whereas this one over here is going to be 2 to the 3rd twice. And if we know from earlier, our multiplication of like bases add our exponents. And with repeated addition, that's just multiplication. All right, so this is 2 raised to the 2 times 3, whereas this is 2 raised to the 3 times 2, or other way around if you prefer. Yeah, we could probably do that. I don't know that I have it set up necessarily, but... Well, I mean, I guess I could just get into Discord. Anyway. Yeah. Definitely. Yeah, let's set it up off stream and then we can then we can do it. Okay, so yeah. So anyway, the Common Core system as it's set up in America, the general idea is that we're going to take this like mathematical concept and we're going to feed it into like super early math. So anywhere from kindergarten all the way to 3rd grade, feed in this basic concept. And then it's going to be a story thread that runs throughout the rest of their mathematical careers until these students reach algebra, reach calculus, whatever. And it's been passed down from class to class to class the exact same way, just talking about it in a different concept. So again, do we want to do like division? Sure, we can do like, 6,372 divided by 87. Right? This is going to be really annoying. I has regrets. Anyway. Ooh, nope, hang on. Wow. 56, 60. Yeah, that's actually going to be 7. That's fine. And in fact, it wouldn't even matter. You know what? That's fine. We'll do 5. So the whole point here is to be like, okay, well, if what we're really doing is this repeated, if multiplication is repeated addition, then division is going to be explained as repeated subtraction. So in this particular case, what we're doing is we're saying, okay, let's take 50 times, because again, here we put a 5 and then a 0 would fill out that number, right? So we're going to just eliminate that because I don't need that right now. We're going to multiply our 87 by 50. You can't see that. We're going to multiply our 87 by 50, and then we're going to subtract that particular number from whatever it is. Well, from 6,372. So 5 times our 8 is going to be, oh man, why am I doing this? 40. And then here that's also going to be with an extra 2 zeros. So we have one place here and one place here. That's going to get us 4,000. Okay, and then the 7 times 50 is going to be 35 with another 0 after it, so 350. So 4,350. Cool. So we're going to subtract 4,350 from this, and that's going to get us our 50 times 87. So this is 2,022. Definitely meant to do that. All right, 87. Well, 87 is going to be 3 is going to be 3. 30 is going to be too many, but we'll put in a 20 for that one. So 20 times 87 is going to be 1,600, and 20 times 7 is going to be 140. So 1,740. Boo. 2. 174 from 202 is going to be 30 is too many, so 28. Right, and this is actually how students would go about solving this. 3. 87 times 3 is going to end up being 21. And 24 plus 2 is 26. Cool, 261. If we go 3 times 261 is going to get us 21. All right, we're too, we don't have enough individual places now, and so what we do is we say, okay, let's add these up. So that's going to be 73 with 21 87ths remaining. 87 is divisible by 3, so that's going to be 7 over 87 divided by 3. Damn it. 29, right? Yeah. 7/29. So our solution here for 6,372 divided by 87 is going to end up being 73 plus 7/29. Right, so what these students did was they were able to estimate, or they were able to find another use for the division algorithm. Instead of just strictly saying, okay, how many exact times do we need to put in for each of these things? I could have done the 7 here in one go. Easy enough. Could have done it. But we ended up you can step into it and get it in multiple tries. This is another thing that is kind of encouraged now, is to make a guess. If that doesn't work, let's try something different and just make converge on the correct answer instead of worrying about getting it right the first time. Okay, so 63/72 divided by 87. Another student might have said, okay, let's divide by 8. 8 times 8, 64. We're pretty close. So this is going to be 80. Right? 87 times 8. This is going to be 6,400. And 8 times 7 is 56. So that's, whoops. No, not 64. It's 640. Wow. Okay, promise. Oh, but no, this would have been 80. Right. Right, so 6,400 and 560. And in our generation, we would have been oh no, we went too far. Now we've got to start all over again. Okay, so they said, all right, let's do 80. Kids in this generation are told, no, you don't need to do that. That's fine. Just go from there. What do you get? All right, well, this is going to be 6. We had to borrow from here, so that's going to be 595, 98, 588. Where are we? I know, I should be doing this in my head. 69, 60 minus 63, 72. I'm just going fast. 588. Okay. Okay, so subtracting these things, I get 588. But that's negative. Okay. Well, now we need to subtract from that amount. So we're in the negative, so we're going to do kind of the opposite. So instead of adding this next number, we're going to subtract from 80 to get the next one. So what do we do? Okay, 8 times, I don't know, 7 will get us pretty close, right? 87 times 7. Right, that's 49. That's going to be 56 plus 4 is 60. That's 609. 609. So now we're adding swings in the other direction. This is going to be 19. And we're in the positive direction at this point. Right, gets us 12 to get from 588 to 600. And then another 12 plus another 9. Nope, not 19. Damn it. Is 21. So now we're out of space again. So 21/87. Oh, look at that. It was the same fraction. Is going to get us 7/29. And then 80 minus 7 is going to be 73. So our answer, 73 plus 7/29. And students get it the same way, whichever way they go. Our generation was taught that doing this thing here and ending up going too far, if we guessed 80 and then we get this thing multiplied out to 6960, it's too high, so therefore we can't do this. The students these days are taught, well, you can do it. It just takes a little extra thought. You went too far, so now what do? Well, we do the opposite. So instead of our answer adding all of those numbers in the quotient column, we're going to subtract the 7 because we went too far, so now we need to back off. Right? And somebody could have done another thing. They could have done, like, let's subtract 6. So if we had subtracted like 80 minus 6 and only subtracted a smaller number, right? So it would have been like 520 something, 520. Having a day. Yeah, 522. Subtracted it, you get a negative in your remainder. Well, it's not a problem either. It's going to be, a negative 66 out of 87 is going to be a negative 22 out of 29. So we subtract 22 29ths from 74. And then we get 73 and 7 29ths. So like all this stuff works. It's just a matter of like how much work do you need to do to get there? And if we do it incrementally in smaller steps, then it's going to take us longer, but overall we can be more confident in the answer. Again, we're converging to the correct answer rather than always getting the most efficient algorithm to do so. Because using the most efficient algorithm to do so might not be something that a student can just see. I could when I was in 4th, 5th, and 6th grade. I got it. My teacher was so happy that I was, constantly just seeing the way that this stuff worked. But half the class didn't get it. And it's not their fault. But at any rate, I'm going to try and kind of push this idea out there that there's not one right way. And the Common Core stuff, as much as everybody rails against it and says, oh, it's awful, it's terrible, I don't understand it. I don't understand what my kids are doing. Well, yeah, because you didn't explore all of this. And Viv, this is where I come in. One of the ways in which I am planning on doing stuff in the future is to make content specifically for not the students, but either for the teachers and or the parents of the Common Core kids. It's this is what they're learning in school, and this is why it doesn't suck as much as you have been thought to believe it does. Or as much as you have been told that it sucks. This is why it is not actually as bad as you have been told it is. Now that I've tipped my hand, I better fix it, or I better do this. Oh no, someone might take my idea. So, for instance, Khan Academy does a great job of highlighting from the student's perspective how all this stuff works, and says here's our Common Core problems that we're going to use for this particular section. That's great, but we're not just going to do this for the student's perspective. My field is math education. So I'm going to go out here and say, this is why this stuff works. This is where it connects to your kids' future endeavors. This is how it works with all the stuff that, all the stuff that you've been taught. This is where it ties in. And so you might be able to see this from my perspective a little bit easier than you can from your kid's perspective, who might be absolutely panicking and being like, my parents don't understand anything. I need help. So that's my intent. We'll see. We'll see how this goes. All right. If anybody has any questions, let me know. Specifically about math, but or about me, my experiences, things I've been doing, projects. Who knows? Got all sorts of cool stuff. I think tomorrow morning, well, at some point, might go for a bike ride, but at some point I'm probably going to start looking into fixing some of the stuff that I've got on my YouTube channel, because it's I hardly ever use it at this point, and I need to. I need to fix some of my highlight reels and things like that that are on Twitch. Try to pull a few clips so that I can get more interesting stuff out there. I know when other people have been trying to call up my clips, it's like, got so few random things. Absolutely not. If you have any specific questions, let me know, or like a section that you might be working on, that sort of thing. In the meantime, I'm going to real quick, I'm going to do another 3-minute ad to knock out pre-rolls, and so that I can top up on water, cycle some water. And if you all have not done so recently, make sure that you get up, walk around, stretch, get yourself some water, cycle it, and we'll be back in 3 minutes. See you in just a couple. Ad break over. Holy crap. Uh, my counter over here still said it had a minute left, so that's a little weird. Anyway, good news. Trigonometry was one of the courses that I spent the most time teaching at the community college. So I ended up becoming, out of all of my 24 colleagues or something like that, I was the person who had taught trig the most out of everybody. And that included adjuncts, that included full-time people, that included people who went back and had been teaching there for 20 plus years. So hey, you got the right person. So if you have any particular questions about trig, like, let me know what. Otherwise, I'm just going to start, like, rambling. Hey, Braylon. Yes, so my spouse is working as a software engineer asterisk in the UK. So I say asterisk because I'm not 100% sure that would be the best title, but it's not really, you know, it's not really my place to question, I guess, what the company is doing. Okay, sure thing, Nep. So she is still earning the exact same amount of money as she would in the US as the UK. Although right now, we just don't have to pay for housing or our kids' schooling. So, like, we don't have to pay those expenses. Well, I mean, we didn't have to pay school in the US anyway because we were doing public. But, so, well, it's not really a fair comparison because, like, we're living now in a minor city, whereas in the US we were living in, like, a very large town. So, like, it's not really that comparable. If we're just doing straight, like, you know, the house we're living in versus the house we were living in, like, we would be paying more now. But again, my spouse was like, well, we're just gonna kind of live in, like, we've got kind of a budgetary range where, like, these are the houses we're gonna start looking for, and then, you know, kind of crept up a little bit from there because, again, we have a housing stipend which pays for rent but also then for utilities, so we don't have to pay utilities essentially. Like, all right. Maine has a fairly low cost of living asterisk because, yeah, it kind of depends. Like, overall, with everything, you're going to have to pay more in the UK, generally speaking, due to the fact that you are living on an island, right? And literally everything has to be shipped in unless it is made here. We do have local foodstuffs. So we do have butchers, and we do have, oh, yeah, whatever. That'll be fine. We do have... All right, whatever. We do have local butchers. We do have local, like, dairies and things like that. So it's not too bad. tips when you... Oh, right, and we don't have to pay tip. So that's another thing, is that the UK is like, you don't have to pay tips unless the service is amazing, because they pay their workers a living wage. Sales tax has a value added tax, VAT, which is oftentimes included, no, sorry, not included in the price, oftentimes. It is 20%. However, that encompasses literally everything. And since we are United States citizens who are working for a United States company that is operating within the UK borders, we do not have to pay value-added tax, provided that that thing that we purchased, whatever it is like hundreds of dollars. So we bought a new TV because we didn't want to bring the one from the United States over here. It was just going to get in the way. And if it got broken, it was just going to be a huge pain in the rear. So we said, all right, let's just buy a new TV once we get there. And so we paid on the order of like $300 for our TV, and then also the VAT popped up, right? So 20%, it's like $60, $80, something like that. Right, I mean, I'm estimating the cost of the TV here. But and then we said, okay, if that's going to cost us, 60 whatever dollars, then we submitted a voucher, whatever. We submitted an intent to purchase, essentially, to the company's office, and the company's office contacts the UK government and says, yeah, they don't have to pay tax on that, don't worry about it. So we got a check that said, here's the money that we're going to spend. Here's the money that VAT would be. And then we only had to pay for the retail price. So we got retail prices on us, and then the check for the VAT came from the company to give to the retailer. So overall, they get their money. They're perfectly happy. We got our object for, in this case, a TV, for less, or for the advertised price and no more. So that was pretty nice. In terms of no problem, Brandon. In terms of depressing, yeah, there's the problem of vitamin D deficiency and SAD, the seasonal affective disorder, which could potentially cause some problems. We do have seasonal affective disorder lamps, which I don't think we technically have any in the house, but whatever. We're going to get them before winter rolls around again. Right now it's springtime. We're rolling into summer, so it's light out until 10 p.m. And it's not even June. So we've got plenty of sunshine right now, but once it gets into wintertime, yeah, seasonal affective disorder is a real thing, and we will have lamps to correct that. It rains every day. Yep, it sounds a lot like Yorkshire as well. If you do move to the UK, I recommend looking into the weather patterns and average rainfall, average sunny days, etc. We are not planning on retiring here or anything like that. I wouldn't say the American dream is dead. I just say we need to get it back on its feet. However, the fact that there are so many ridiculous issues with gun violence and things like that, we're pretty happy that we've got our kids out of the public system right now. No offense, but weaponry in schools is just not a thing that we want to deal with. $26? Yeah, well. Also depends on where you get it from. Because if I'm gonna just be looking for something quick, I'm looking for a sandwich vendor. Okay, so we're gonna go with Nep's question from above, which is how exactly do we work with like trigonometry in general? So there are two approaches that generally will work. They're often called the right triangle trigonometry approach and the unit circle approach. I like to use both. Not less than $20. Yeah, it can happen. Okay. So the way that we work this out is that we say if we're going to look at any, you know what, let's back up. Braylon. I'm going to tell you this, man. That man does not want anything except anything that makes himself look good and enrich himself. He does not care about anyone or anything else, I promise you. He did not care about anyone or anything else but himself in the 60 plus years that he's been doing anything in the public eye. I promise you. Okay. If we back up to this, and if you're like, oh, you must be for buy it. No, not really. I just, no. A piece of bread would be better than that guy for president. TFG, man. All right. So geometrically speaking, what we had going on for a long time here is that the ancient Greeks were looking at, like, how do we formalize geometry? And so this is really what Euclid was all about, was trying to say, let's formalize all of our mathematical concepts. And so Euclid, his job was to start with, I don't have the elements with me, it's packed. The basic geometric principles start with what are some of the most basic things we have. So most basic thing we have is just a point. So something which has no other dimension or no real dimension to it, just an object in space. It has no length, no width, no breadth, nothing. Right? And then if we add another point in space, this allows us to then build a line between those two things. Now, in Euclid's day, a line actually just meant the segment that existed between these two things. In our modern parlance, we also just extend that infinitely in both directions. In his day, that wasn't really what it was. It was just that you draw the line between those two things and you stop. Okay, and then by building out a third point with another line, right? Again, either infinite or just contained, doesn't really matter. You form a set of angles. Euclid also proved then, and this was probably proven well before his time, proved that the vertical angles, the angles that are opposite each other in this diagram, are going to be equal to each other. and that you can get 180 degrees split between the two lines, the two angles along any one line. So got that, 180 degrees going that way, 180 degrees going that way, diagonal 180 degrees going that way, 180 degrees going that way. So it's all the same stuff there. Yikes. Yeah, I'm waiting for that bubble to burst. We just sold our house, so like it's official, it's done. We now have the money in our bank account, which I gotta say looks pretty good. My spouse goes onto our investment accounts and looks at the amount that's in our account and is like, we're going to transmit this amount of money into this investment account. And we're like, that's a really big number. So we have left the United States. We're currently in England. I mean, I think you knew that. But yeah, we're not permanently leaving. We're planning on coming back after 3 years. We'll see how things go. But we want our kids to do their we want our kids to do the rest of their school in America, but question mark. We'll see how things go in the next 3 years, and if they're both like abso-effing-lutely not, then we'd just stay here. Well, yes, but that's the other thing, Brethren, is that, again, we're still making U.S. money while living here. So... sort of. I mean, she's got a pretty much guaranteed job as long as, like, can't get into it too much, but yeah. Well, then let's make it better. Alright, so we've got our lines with points. We've just created angles. I'm also going to recommend this to everybody. It is currently getting worse, I will guarantee you, but that is also mostly because we are not standing together, banding together, and actually figuring this stuff out. Everybody's like, oh no, we're all separate from each other. Help, help. Somebody. And then somebody went out there and decided to throw you a bone without actually giving you anything of substance. Right? If you want to be ruled by fear, certain people are very happy to do that. Yep, and there are a lot of places that are trying to prevent homelessness and trying to help out people with that. Okay. So we're forming these angles, and Euclid's major contribution, no, that's a lie. Descartes' major contribution to this was to say, hey, I noticed you guys have a lot of, and it wasn't even Descartes necessarily, but Descartes came up with the Cartesian coordinate plane, and he said, like, we can get a lot of this stuff that we've got and we can put it onto this coordinate plane. And in doing so, now we've got these XY coordinates that we're working with. Certain other people who are working on trigonometry were then going to say, okay, now that we've got a coordinate plane with the Cartesian coordinate plane, we can now formalize geometry by into the Cartesian plane by saying, let's take the one part of this angle that we really want to standardize and put it smack dab in the middle. Yes, that's right. This is going to be our vertex. So our vertex gets placed from just this random point out in space to the origin point. And our second, that's terrible. Let's pick a color that's more obviously different. Nope. A. Let's take our second point and we're going to put that somewhere along the x-axis. This is going to be a standardized line then. This is going to be our initial side, which is then going to be just wherever we put this thing. We say, okay, it's going to be the line or the ray, if you want, that connects our vertex to whatever standardized position we're using along that initial side. Okay, and then we're going to take, man, we're going to take this point here. That's not helping. And we're going to stick that out in space. It's going to open as far as it needs to get to that particular angle. To make that particular angle. So this size now here becomes this size here, and it is directed, which means that we're going to choose a particular direction to move in. So counterclockwise is going to be our positive direction for our angles. They will always open that particular way. Now this is what's called the terminal side. Will terminate along a particular radius. We're just going to have it be equal to 1. So we have a radius of 1 on this particular unit circle at a particular location, x comma y. Okay. And then when we draw these in, okay, and then we have particular locations, which are going to be on the circle. And this makes it real easy to find, again, locations for all these things. So if we have a radius of 1, if we're just going to the right, yeah, that's to the right. Sorry, I'm backwards. So if we go to the right, I got to remember, this is like me standing up in front of a room. So when I was teaching my students, I was always doing things opposite the way that I normally want to do it. And so it makes it a little more obvious. Anyway, yeah, so we're moving to the right one and having the edge of the circle over there. That's 1, 0. Our vertex, our center, is at 0, 0. It's the origin point. Of course it is, right? If we then go up, that's 0, 1. To the left is -1, 0, and down is 0, -1. So, easy enough. Okay, then when we do that, we say, okay, if we want to be at any particular angle, just off in space, right, what are we going to do in order to find those positions, those XY coordinates at any of those particular locations? Okay, so this is where it gets a little bit maybe trickier, maybe harder. We'll see how it goes. So the easiest places to find angles, and really we should back up a little bit and say, okay, what are angles going to be in this particular setup? Well, if we go back to ancient Babylon, the way that they had set up angles was that they wanted to start with a circle and say, like, okay, how many ways can we split this circle up in order to allow us to see, you know, small gradations of movements around the circle. And so their natural choice was their base. They said that, okay, here we're going to have a, like, no angle. That's fine. Don't worry about it. We won't call it a number. We have no angle. And then if we open further and further and further, we're going to have all these different possible angles. If we make it all the way back around, this should be 3600, which is 60 times 60. Their base is 60. This created a bit of a problem because 1/3600th of this circle is really hard to draw. It is in fact smaller than that distance between those two lines that you can see there by a significant margin. It's like less than a quarter of that. I don't know exactly what it is, but yeah, like that distance between those things, it's really small. It's not going to work very well. So they were like, all right, let's just make it that. So they took a factor of 10 out of them. They said, okay, it's... Well, it made sense because their base was base 60. Where are my books? Yeah, I don't have my cuneiform books. But in cuneiform, right, the way to draw the numbers was to put stacks of... I actually did this, by the way, with a triangular crayon and a glob of Play-Doh. I recommend this. But you take the triangular crayon, which you can get from #NotSponsored Crayola, or some other company if you prefer. You can get triangular crayons. They're easier for little kids to grab. And they encourage correct grip a little bit better. So if you grab onto it and then instead of writing, right, you flip it around and put it in your thumb like this. Like grab it with your fist and then put your thumb on top. This makes a nice little stylus that if you have a glob of clay, you can tag them, sort of moving around and tapping the stylus into the clay. It can get you something that looks more or less like these things. So this is 3. Six. Oops. And 9. Eventually you start making like cross hashes like this, which go across it, and it starts getting you larger and larger numbers. It gets crazy when you start like doing all the numbers out. Eventually this goes to nope. Something like this, which was, this is the number of 1s, and this is the number of 60s that you have. So this one together is going to be 61. This one here, I don't even remember what this is. This is freaking crazy. But yeah, this would be like a bigger number, and it keeps going from there. Anyway, cuneiform. There was a problem here, because if you leave a certain amount of space between the number, it could be 61, or this could have been 60 squared, so this could be 3601, depending on the amount of space you left. Again, creates a little bit of a problem. So is it 61 or is it 3601? I don't know. So then when people actually started using, like, the Babylonians had a really good system of mathematics, and they taught mathematics to their scribes at a fairly high level. You know, compared to the ancient Greeks, they were pretty much on par. It's just that they didn't formalize their, like, proofs and stuff. Or at least not as much as the Greeks did. They were much more interested in finance and architecture than they were in theory. So the scribes and the architects were useful to doing this stuff. Yeah, right. Yeah, and then you got to put it on the tablet, and then you got to make sure you fire it in the kiln for a while, so when you take it out again, it's not going to just get smudged every time. Dad, come on. You put it in your pocket. I need to call Bathsheba. Good times. So they didn't know, like, what to do with this until somebody was like, hey, wait a minute. If we put a symbol in between, this is going to allow us to say this is just like a null space, an empty space. So in this case, this is definitely 60 squared. We have no 60 to the firsts, and then we have a 1. So this is definitely 3601. So the Babylonians didn't actually have a number for 0, but at least, you know, they figured out a way to make a 0 placeholder. It wasn't until the Indians eventually came up with the 0 number, also known as crap. I knew this. I swear I knew this less than a month ago. Friggin' A. Shunya. I didn't even actually get the thing up. There it is. Found it now. Yep. So there are... Yeah, okay. So 2 mathematicians are credited with the concept of zero, like coming up with the actual number, which again represents shunya, or the emptiness, which also can be thought of as a completion of the circle in samsara and becoming reborn again, things like that. As such, zero has a intimate relationship with infinity, the idea of infinity. The 2 people credited with the concept of zero are Aryabhata and Brahmagupta. So those are our 2 famous mathematicians from way back when. Who again generally get the most credit for coming up with the concept of zero itself. Okay, so instead of doing 60 times 60, which again gets us our 3600, they shortened it a bit and said, okay, we only need 360. We'll cut it by a factor of 10, and, you know, it works well enough. And in theory, you could also make it like 360.0, and then that would be able to, you'd be able to figure it out well enough. They never needed it to be as accurate as like tenths, just because like back then measuring instruments weren't really that precise. Yeah, they did okay, but when it came to like building astronomical devices and astronomical measurements, then they started needing like more exact angles. But generally speaking, you know, as close as they could be guaranteed to get was starting to get into the like single, what we call single degrees. Okay, so that's 360 degrees. But here's the thing. It's kind of arbitrary. Shrug. Right? Like 3,600, 360, 5,000, like any number you want to pick, you could just pick a number for no particular reason or because you like it. If we base things off of this ancient Babylonian system, like, okay. Right, and this is also one of the reasons that I got so far into this, was because I was interested in math history and started getting into it and started telling students all the stories and stuff like that. And they were like, oh, well, this is really kind of cool. You know, it engages the students who are more interested in history than they are in mathematics. It engages the students who are interested in mathematics because they want to know the history behind everything. Even if they don't like history, they like mathematics. Sure, now they like the history of mathematics, which honestly was my in. I did not like history, generally speaking, because a lot of it, I have kind of the same feelings toward history as I forget who it was. There was a interview that was being conducted with Douglas Adams and Sir Robert Patrick, maybe, of the Royal Society, and he was saying, like, you know, the history of science is basically irrelevant. If one person doesn't find something, then someone eventually will. I was like, yeah, exactly. If it wasn't Euclid, somebody would have figured out, or somebody would have formalized Greek mathematics around the same time as him. It would have only taken maybe another 100 years or so to like get somebody who was sufficiently motivated to do it. And keeping in mind, this is like 500 years after Pythagoras, so it wasn't him. Goodness knows he was not interested in that, considering how much debauchery he was getting up to in his day. That also usually gets a "wait, what?" from students. Okay. So anyway, if we want something that is non-arbitrary, then we say, okay, what measurements are non-arbitrary about this thing? Well, we've got a radius. And we've got circumference, which are really the two big ones. Getting insects from outside. I'm wondering if something just got me in the nose. Could just been a hair, I guess. I don't know. All right. So in terms of circumference, we have a relationship between circumference and radius, right? Circumference is equal to 2 pi times our radius. And if we let r be equal to 1, then our circumference here is just going to be 2 pi. So, like, cool. Let's go down here, and we could say all of our individual sectors, so all of these areas that we've created within this circle, can now be measured not just as an angle in degrees, but also in an angle as far as how many radii are we traveling around the outside of the circle to get to whatever location we're at. And it doesn't actually matter what the size of the circle is. So here we can either be at 0 or we go all the way around and we get to 2 pi. Right, if we only go halfway around, that's going to be pi. If we only go a quarter way around, that's pi over 2. And at the bottom here, this is going to be 3 pi over 2. Some other mathematicians have been interested in making this in terms of tau, which is just you go from 0 to tau, 0 to 1. So 2 pi is equal to tau, and then you're just saying how many, like, what fraction of the circle are you going around? And that's your tau. That's your angle. It works. It's fine. But if you want to do that, then you've got to redefine all of trigonometry to be based on tau instead of pi. And, you know, it's fine. It works. It's just a scale factor of 2, basically. Okay. So then we've also got these angles here. Close enough. Right? So now if we divide each of these halves up into halves, this is going to get us pi over 4. And then we can count, because these are all going to be equal going around. So starting from 0, we go to 1 pi over 4, 2 pi's on 4, which is the same as 1 pi over 2, 3 pi's on 4, and again, I'm just counting and using pi over whatever as a unit. 4 pi's on 4 is the same as pi, 5 pi's on 4 gets us down here, 6 pi's on 4 simplifies to 3 pi over 2. 7 pi's on 4 gets us over here. And 8 pi's on 4 gets us back to 2 pi. So we're back at the beginning. Okay, and then if we cut this segment into thirds and actually cut the segment around here into thirds. Yeah, there's a reason. We'll talk about it. Hey guys, hang on one sec. I got a visitor. Oop, kerclunk. No, give me one sec. Alright, I'm gonna hit the button and we'll go for 3 more minutes and be right back. Alright, thanks for sticking around. Yeah, that was a lot faster of a visit than I was anticipating, so apologies for hitting the 3 minutes, I suppose, but yeah. You never know with them sometimes. Okay, so what we've just done here, and I popped in a couple of these while we were out, is that we've now split our pi into 6 equal parts. So here, this is going to be pi over 6. And now we can go, again, the same counting mechanism. This is going to be 1 pi over 6. 2 pi's over 6 is going to be pi over 3. 3 pi's over 6 is equivalent to pi over 2. 4 pi over 6 is equivalent to 2 pi over 3. 5 pi over 6 is here. 6 pi over 6 is just pi. 7 pi over 6 is here. 8 pi over 6 is is equivalent to 4 pi over 3. Oof. Yep. 9 pi over 6 is equivalent to 3 pi over 2. 10 pi over 6 is equivalent to 5 pi over 3. Damn it. Whee! And my head's clear. Good. 11 pi over 6 is going to be here. And 12 pi over 6 is back to 2 pi. So with that, now we see we've got all of the individual values that we're honestly going to need. I also usually include the other ones. What? That was not what I wanted to do. Now you can see how straight I draw one and just jab out like this. Here. Here. Nope. Here. And here. And it's off a bit. All right, these are our pi's on 12. And if we're honest here, right, this is our base unit. This is going to be 1 pi over 12. 2 pi over 12 is pi over 6. 3 pi over 12 is pi over 4. 4 pi over 6, 4 pi over 12 is pi over 3. 5 pi over 12 is its own thing. 6, 7 pi's on 12. 8, 9, 10, 11. 12, 13. 14, 15, 16, 17. 18, 19. 20, 21, 22, 23. And 24 pi's on 12 is back to 2 pi. So I prefer to have students build this one out first as we go through and say like, okay, these are all of our kind of base units. It's a multiple of pi on 12. Yep, exactly. But the thing is that the pi's on 12 that are not simplifiable, so our 1, 5, 7, 11, 13, 17, 19, and 23 pi's on 12 are really hard to find any sort of angle stuff for until we get like halfway into the course. It's like a third maybe, but nonetheless, it's for me it's unit 2. So we look at this and we say, okay, we can split it up in terms of pi's on 12, right? Our pi value, 180 degrees, ends up getting split into twelfths. Those are 15-degree segments if you're going by the degrees. So, yeah. Not multiples, increments. Okay, they're all 15-degree increments going all the way around if you prefer degrees. If we're doing radians, they're all pi on 12 every single time. And a reminder, this is pi on 12 radians, which means that this is 1/12 of... that's not true. Sorry, pi on 12 is approximately 1/4 of a radius measurement. So whatever your radius measurement is, it's like give or take 1/4 of that. Again, 3.14159 over 12. Okay, so when we do this, we're going to say now, well, depending on how big the circle is, that's an actual different distance. So if it's, unit 1, we're on the unit circle. And so that distance here is this arc. If it's way out here, it's the same arc, but now it's further away, so the actual physical distance is going to be bigger. So, like, how do we do that? Well, if we look at this, right, we've got 2 pi times r was going to be our circumference. And some of you may already see it. Circumference is equal to 2 pi times r. So what about, like, any old random arc length? We'll call it s. Well, we've got our radius here, but that just meant, like, how far out do we go before we make that arc? Circumference is going 2 pi. That's the whole distance all the way around. So, like, half of it would only be pi. A quarter of it would only be pi over 2. You know, some random measurement like here, wherever that is. If we went like that, we're going around the outside of the arc here, it'd just be the radius times whatever this thing is, right? So this is our angle. Right? Our arc length, the length around the outside, is just going to be our angle in radians times the number of radii. Okay, I'm going to take this out very carefully. Probably don't need to. Okay, so that's going to be what we get for this. Now, what we're going to do is we're going to say, now we want actual, like, physical locations in terms of how we get nice values on this circle. Okay, well, how do we get nice values on the circle? And I use the word nice in quotation marks here because it kind of depends on what your definition of nice is. We do know that if you should just go out with, if you have any particular triangles that you know, right? 45, 45, 90. Is a particularly nice kind of triangle. It has an angle which is half of a 90-degree angle. So we know that 90-degree angle is pi over 2. So half of that arc length is half of the angle, pi over 4. Same deal. So a 45, 45, 90 triangle, we can look at this and say, all right, I know that my radius is 1. Or you can just make it r if you wanted to, but we'll stick with unit circle for now. Well, how much is our x and y coordinate going to be worth? If we remember from geometry, anytime you have an equal angle in the same triangle, the opposite sides to those angles have to be the same as well. So in this particular case, we've got this 45, 45, 90 triangle. Wow, okay, close enough. X, y, and 1. If the angles are the same, then x is equal to y. And so we end up with x and 1. From the Pythagorean theorem, we know that x squared plus x squared is going to be equal to 1. So this is 2 x squareds, which means that x squared has to be a half, which means that our absolute value of x, right, the actual value that we have here, has to be the square root of 1/2, which is equal to square root of 1 over square root of 2, or just 1 over the square root of 2. Or if you insist, square root of 2 over 2. We can rationalize the denominator, multiply by square root of 2 over square root of 2, and get that. So either way we get with this, we get these values. And interestingly enough, right, this is the absolute value of x. So the distance that we travel from the origin in the x direction needs to be square root of 2 over 2, or 1 over the square root of 2. Now, if that's the distance that we travel in the x direction, that doesn't matter which direction we go.
Raiding party!
Raiding party! Hey, Stucky, how you doing? Good evening and welcome, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are working on some trigonometry, so kind of the introductory section of trigonometry. How exactly are we going to get this baseline? Good evening. How are we going to get this baseline knowledge of how trigonometry works? So we're going to start, well, we're starting with the unit circle and then going to work our way up from there. So good evening, everybody. Hi. Phobos, how you doing? This is the information for Ian Stucky. If you have at all any interest in hanging out with other cool math type people, that is their information. We have Stucky has a Discord server, and that is the Twitch channel up above. And Nep, double dipping. Always encouraged. I will say, right? Always encouraged. Some people think it's a bad idea. I definitely don't. Getting any and all information that you possibly can. Right? So this means that our x can be either a positive or a negative root 2 over 2. Now that also means that since x was equal to y, that y is also either positive or negative root 2 over 2. And this then means that we can go in any one of these directions. All right, now I will say, right, if it said, technically I said x equals y, we didn't really have to just be x and y being the exact same number. They could just have the same value. So realistically, it was just that the absolute value of x and the absolute value of y, their distances, were going to be the same. So even though we did say originally x and y were the same, that's not really what we meant. That was only true for the one in the first quadrant. Let me actually pull my mouse closer so I don't keep having to lean off screen. Right? Our x and our y have to be the same distance, but we could have been going down here into quadrant 4, make a 45, 45, 90. Could have gone into quadrant 3, could have gone into quadrant 2, anywhere we wanted. Our x and our y just have to have the same distance. Okay. So y is going to be then equal to plus or minus root 2 over 2 as well. So this gives us 4 different possibilities for having these sets of coordinates. Again, here we get root 2 over 2 comma root 2 over 2. Whatever. Here we get root 2 over 2 comma negative root 2 over 2. Down here we get negative root 2 over 2 comma negative root 2 over 2. And up here we get negative root 2 over 2 comma positive root 2 over 2. And again, we could have done this as 1 over the square root of 2 instead, but Okay, so that's how we're going to work on 45, 45, 90 triangles. So then the other one is, well, we do know some sort of relationship that exists with equilateral triangles, right? So it'd be really nice if we could set up an equilateral triangle inside of our unit circle. Oh, what do you know? We can. Right? We know that equilateral also means equiangular. And so if it's equiangular, then they have to be 60 degrees on each corner, which also means that these are going to be, 60 degrees was 360 divided by 6. So now it's 2 pi divided by 6. 2 pi over 6, we did that earlier. It's pi over 3. So we can make pi over 3 on any one of our angles there. And looking at it from that perspective, let's chop this thing in half this way, because again, that makes us have a right angle triangle now. And for our equilateral triangles, if we're doing this on, let's do it on 2 pi over 3, because otherwise we got some stuff that might be in the way. Here, this is going to get us an equilateral triangle. If you're not convinced that, oh, well, this one's not going to work, like, how do you know that that's going to land exactly on, this point out here? You might say, look, you just invented that. I don't believe you. That's fine. We'll do it this way instead. So a 30-degree angle is pi over 6. So we'll go pi over 6 up and pi over 6 down. I know for a fact that this point here and this point here have now landed in the same horizontal place because their angles are equal, going up and going down. Again, this is our pi over 6 here. This is pi over 6 here. So these are equal, which means that our sides must be equal here and here, right? Split along our x-axis. Okay, well, split along the x-axis. If our equilateral triangle, and you can tell this is not an equilateral triangle just by looking at it. My drawing is terrible, but nonetheless. We're going to say, well, our radius was 1, so this radius is 1, and since it's an equilateral triangle, our third side must also be 1, which we just split it in half, so the top one's a half, the bottom one's a half. Cool. Those are our y values for those 2 points. Positive 1/2, negative 1/2. Now, about the x values, that's where it gets a little harder, because now we got to look at, like, how far over is it? It's not 1, it's not a half, like, well, these are vertically distance of a half. That's another thing you can check, by the way. Does it even look like a half? We go across like this, check like that distance here, say, yeah, more or less. It's close enough. Okay, but enough of that. So what we're really concerned with in terms of like actually getting these coordinates is that we've made some yeah we've actually made this equilateral triangle, which then gets split in half. So now we've got a half and a half up and down. Then that leads us to a picture, which we can draw somewhere like this. So we've got a half here and a 1 there. And now we don't know what the x value is going across. I want to remind you that this is the same thing if we took this whole thing and rotated it and made it connect with 2 pi over 3 or pi over 3 or anywhere else on the circle. Like it's the same triangle, it's just how you organize it. It's going to look a little bit different. So we do this, and we say, all right, here we have x squared plus 1/2 squared is equal to 1 squared, which is just 1 again. I guess I didn't do that over there, but you get the idea. X squared plus 1/4 is equal to 1. Subtract 1/4 from either side using my patented method here of subtracting or adding equations. Definitely not patented. X squared is equal to 3/4. Take the square root of both sides, you get the absolute value of x is equal to √3 over 2. √4, right, makes you 2 on the bottom. So now our x values are going to be plus or minus √3 over 2, depending on what quadrant you're in. This is not difficult, like with a lot of this stuff. So when you look at it, most of the time what you're going to think about is like, what are the values in the first quadrant? That's it. You don't have to worry about the values in like the whole rest of the circle, because as long as you know what the scheme is, you know what the values are. Right, so here, now getting to know the scheme might be the hard part, but if you're doing it the way that I'm showing it here, where you're like, I don't remember what this is, what kind of triangle does it make? That's probably the easiest way to think about it. Or at least for me, but... All right, so here, we're to the right. This means that x is positive. It's √3 over 2. Y is positive, it's up, is √3 over 2 comma 1/2. And also, at pi over 3, this is the exact same thing, it's just flipped this way instead of flipped this way. Again, we make that equilateral triangle that's centered there at 0, 0, 1, 0, and now pi over 3 up there. So this is going to be x value of 1/2, because our equilateral triangle gets split down the middle. Our x value is 1/2, and our y value is now that tall value √3 over 2. I know it's really disorganized. And then we just go around the whole circle, and you say, okay, well, x is going to be positive this way. Quadrant 1, quadrant 4. X is going to be negative this way, quadrant 2, quadrant 3. Right? That's just left and right. You know that x is positive and negative, respectively. Right and left, damn it. And you know that y values are going to be negative down and positive up. And so your y values split along that x-axis in quadrants, 1 and 2 it's up, and 3 and 4 it's down. So your y values are positive in quadrants 1 and 2, and negative in 3 and 4. You don't have to memorize stuff. Just think of how it works in terms of like, what are my coordinate systems? Okay, well, x is going to be how far are we left and right, and y's are how far are we up and down. And it doesn't have to be such a stressful thing. So many people freak out about all sorts of little stuff and try to memorize it, and it's like, no, you're not going to memorize everything. It's just not going to work. So here at least, and in everybody else's that works on Twitch most of the time, again. Shout out everybody from the Chads. Penn Center. Dawn does math. E to the 2I pi, that's Zach. Penn Center. Ian Stuckey, again, thank you for the raid. Obi, that's me, at Nsimplex Pachinko. Danny Highway, and Dr. Gold at Actual Education. We are the 7 main math streamers here on Twitch who have kind of banded together and say, we're doing this. So we're slowly building a following amongst us, and highly encourage you to go seek out anybody that you can, to try and find more knowledge, more math, more goodness. We also have many other educational streamers whom we are big fans of. So we have, oh goodness, Muhoodles does astrobiology. We have Sci-Ants streams, who are 2 microbiologists who are mostly working with ant colonies. Go figure. Volcano Doc and Rock It Sage are volcanologists, and both educators. Yep. I have several more, but I'm blanking on it at the moment as far as what, like, everybody's stream names and their... Physics and Depression. Talks about physics, mental health. And again, there's a bunch of people. Physics and Depression also does a bunch of math through doing physics, naturally. So any of that out there, if y'all are interested, feel free to seek anyone out to get more information about anything, and yeah, tell us about them, tell them about us. We'd love to hear more. Also, the Knowledge Fellowship, TKF, is a location that you can go to get more information. Yep, here we go. So we can also... Oop. Okay. I don't have permission to invite people to TKF. So I couldn't remember if it's more of a streamer's location. Anyway. Well, either way. I highly encourage you to seek out anybody who's doing any sort of educational stuff on Twitch. And again, let us know about them. Because we would love to hear about who they are, what they're up to, and what they might be doing in terms of mathematics. We've gone pretty far afield tonight. Just to recap for anybody who wasn't here earlier, we did talk about a bit of calculus. I had done the general derivation of a logarithmic derivative, and I worked with, I posted this on Twitter because somebody was asking, like, I just don't understand where this, like, natural log of a comes in, where the base, natural log of the base comes in. So I popped up that. Then we started talking about different versions of, like, how to do mathematics. We have Vedic, the classic American, and the British versions. I learned the classic American version, the carrying up top. My kids are now learning the British version with the carrying down bottom, which both my spouse and I looked at and went, huh, Yeah, that's way better. The Vedic, which uses the carries at the bottom and then immediately uses them, so you can get everything done in one line. And the American Common Core, which I am now becoming a proponent of due to the fact that it has far-reaching applications, specifically into just doing algebra. Like, you can eventually say, like, hey, by the way, if you know how to do this easy stuff that you learn in second grade, you can do this harder stuff now, which you are learning in algebra. And then we started talking about geometry, or trigonometry, starting with the geometric definition. Okay. I mean, yeah, sure, you've got a lot to catch up on, but at the same time, like, I think you said, Nep, you're getting ahead of it, right? Like, you're not in trigonometry now? Question mark? Okay, and quick recap for anybody who is interested, right? Our original definitions of points and lines and angles and stuff like that really comes from the ancient Greek, which itself is built off of the ancient Babylonian texts. The Babylonian texts which came up were really, in a lot of times, like applications. Here's how to do things. We need to tell you the process. In Greek times, Euclid especially, but several other people, were interested in formalizing the entire approach. That's right, Calc 1. Euclid was interested in formalizing the approach, and so tried to make sure that everybody kind of understood what solid ground we started from, and then they could build off of that from there. So a lot of the trigonometry that they had was built out of the extremely basic ideas. So again, Euclid was building this formal approach from ex nihilo, basically. Or no, that's not true. Ex axiomata. So from basic axioms of mathematics, what can we then build? He got all the way to building three-dimensional objects and doing all sorts of crazy stuff at the end of the 13 books of the elements. The Babylonian system was based off of their number system, which was a base 60 number system. 60 squared got them 3600. So at some point they were like, yeah, 3600 will be our base unit for the circle. And then they were like, yeah, that's too many. So basically they cut it by a factor of 10 and said 360.0 can get us at 3600 as a whole. And then they could split up this into much smaller, or much more reasonably sized segments. Even 1 degree is somewhat reasonable. All right, then René Descartes came around and formalized everything onto a coordinate plane. And then the various people came along and did like, hey, let's look at this unit circle in terms of where we are on this circle in terms of a coordinate system. So we've got these 15-degree increments. We're trying to figure out exactly what to do with this now. And then along come a few different people, and they say, you know what we need is functions which are going to describe the values that we get in terms of the angle that we're at. So this ends up being like, if we find the x values or the x positions as a function of our theta, the angle at which we are starting, or then a y value as a function of the angle where we're at. on this circle, then we can build functions which are then going to be able to allow us to get like new ideas. So we'll work like it's a little bit out of range, but whatever, it's fine. So here we start with our theta and our y values. This is going to go very much longer than this. Just keep going. All right, so we got 0, pi over 6, pi over 4, pi over 3, pi over 2. Yep. I'm not kidding, by the way. This is going to be 2 pi over 3, 3 pi over 4. Yes, this is a little overkill, but I just want to, show some of this pattern so that it gets pretty obvious, like what it is we're actually doing here. All right, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2. And if anyone's like, hey, that's a really interesting pattern that you've got there with the 7 over 6, 5 over 4, 4 over 3, 3 over 2. Like, a lot of this is just kind of coincidental in terms of the numbers that are being used specifically. How dare you? Yeah, I know. So I wouldn't read too much into it. It's just like the fractions that you're adding happen to work out with numbers that have some similar similar properties. 4, 5 pi over 3. 7 pi over 4. 11 pi over 6. And 2 pi. Boop. Oh no, did you not like that? Yeah, we're okay. Okay, I don't even know where we are right now. Cool. Perfect. That is about as close as we're going to get. I'm not going to dare even try to do that again. All right. So if we look at let's go with x values here, right? We're going to start with 1, then it goes to root 3 over 2, root 2 over 2, 1 over 2, 0. Then it starts building into the negative region. This is going to be, I didn't actually do 2 pi over 3, but this is negative 1/2, negative 2 pi over 2, no, not pi, negative root 2 over 2, negative root 3 over 2, and then negative 1. Okay, so 1, root 3 over 2, root 2 over 2, 1 over 2, 0, negative 1 over 2, negative root 2 over 2, negative root 3 over 2, negative -1. All right, then 7 pi over 6. We're just going to be repeating the same values because, again, these triangles are the same thing. They're just in opposite quadrants, depending on your definition of opposite or perspective or whatever. So it's fine. All right, -√3/2, -√2/2, -1/2, and 0. +1/2, +√2/2, +√3/2, and 1. And same deal now with the y values, only here with 0, we were along the x-axis, so our y value was 0. At pi over 6, this was 1/2. And then √2/2 at pi over 4. At pi over 3, this was √3/2. And at pi over 2, this was 1. And then at 2 pi over 3, it was √3/2. 3 pi over 4 was √2/2. 5 pi over 6 was 1/2. And pi was 0. 7 pi over 6, we get into quadrant 3, so now it's negative. -1/2, -√2/2, -√3/2, -1, -√3/2, and again, repeat. -√2/2, -1/2, and 0. Okay. So then what we want to do is to create graphs. Which are going to give us these particular values. All right, this is all freehand, so like it's going to be close, but ugh. It's kind of close. That's better. All right. Now the way that I graph this, if I'm honest, I'm not doing all this. This is a ridiculous amount. My favorite is actually the animation of what happens when you trace the, this way. When you trace the point along the circle, and then it shows on 2 bars what the y position and x position are as the point moves around the circle. It'll actually trace like, you know, like this, whatever it's going to be. And then from that, it actually shows you the curve that it makes. It can actually start like sending it out into space. It's much more obvious when you see it like that. So the way that I'm going to do this is I'm going to say this is 2 pi. This is 0. Halfway between, give or take, is going to be pi. Pretty close. Halfway between those, we're going to get pi over 2 and 3 pi over 2. Halfway between those, we get all of our pi's on 4. Now, for this stuff, this is our x values, right? Our x values graphed with our angles. So this is our theta. This is x as a function of theta, or we call it f of theta. So this said we are going to take at 0, theta equals 0, going across. Our x value going up is going to be 1. And if we go all the way to the end at 2 pi, we also get 1. Too high, I think, but that's probably better. All right. The only reason I'm understanding that and getting it so fast is years of practice. Okay. All right. Halfway in between that is pi. We have the opposite value. This is -1. Halfway between those values are going to be our pi's on 2, pi over 2 and 3 pi over 2, which are zeros. And halfway between those are our pi's on 4, which all have values of root 2 over 2, whether positive or negative. They're obviously going to be either, they're going to be between these individual points. So pi on 4 is going to be up, 3 pi over 4 is going to be down, 5 pi over 4 is going to be down, 7 pi over 4 is going to be up. Because they have to be between these values. There's no extra zeros anywhere or anything like that. Okay, so 1, we know that that's going to be the case. In addition, the value of root 2 over 2, or 1 divided by the square root of 2, you can get out of your calculator. The value of the square root of 2 is 1.414. All right, I just know that off the top of my head because I've been working on it forever. Right, so 1.414. If we divide that by 2, that's 1414. It's 0707 is half of it. So 0.707 which is not halfway, but just under 3/4 the way up from our 0 to our 1. So just under here, which then also happens over here at 7 pi over 4. And then on the way down, it's doing the same thing. 3 pi over 4 and 5 pi over 4. It's just above, meaning towards the center of those particular positions. That one's not right. Uh-oh. Sounds like pretzel stopped. Yep. Okay. So, with that, I can now say, all right, these are going to follow the same sort of pattern. It's going to be curved. It's going to be continuous. So we know it's going to look, vaguely speaking, something like this. Oops. Righto. So that's one. All right, and 2, we're going to go like this. We're going to go. This is going to be 0. Still theta, but in this case we want y, or g of theta, whatever we want to call it. Again, here's 1, -1. Nowhere near low enough. Okay, and again, here's 2 pi. Here's pi. Pi over 2. 3 pi over 2. Pi over 4. 3 pi over 4. 5 pi over 4. 7 pi over 4. And again, with these, now I want to graph 0, 0. And again, 2 pi 0. Now we've also got pi 0. And then we've got pi over 2, 1. And 3 pi over 2, -1. Followed by pi over 4 and 3 pi over 4 have our 0.707 values. So this is up here. This is up here. And 5 pi over 4 and 7 pi over 4 have our negative 0.707 values. Here and here. Which again, okay, so we get something that looks like this. Now, these are what are called periodic. Because if we then continued this pattern, and wait, what do you mean continue? Yes, if we went beyond 2 pi, because of course we can, right? 2 pi plus another pi over 6 would get us to, that's 12, so 13. 13 pi over 6 would get us back to root 3 over 2 again on the horizontal value, and 13 pi over 6 would get us to positive 1/2 on the vertical value. And then we could just keep doing this over and over and over again. To say like, okay, this is going to be 8, 9 pi over 4. Would get us a root 2 over 2 by root 2 over 2. Any number of rotations that we want to go, that's going to then add more to this, and we're going to end up with all these same values all over again. And this is the nature of a periodic function. Regardless of, what kind of function it is, what we're going to do is we're going to go some amount of distance horizontally, and we're going to end up back at the same function values over and over and over again in the y direction that we had in the first period. So this is going to be our primary period, essentially, from 0 to 2 pi. And say, like, in this first rotation, here are the values that we get for this. Makes it really exciting to work with, because it's like, well, if it's periodic, then I can just repeat this. Yeah. This is kind of the way that your car's engine will work. So it will go up and down in this particular pattern thousands of times per minute, RPM, right? Rotations per minute. And if you increase or decrease the speed, then obviously it changes exactly how long the period is. But if you maintain the same period for any amount of time, you don't change the gas. Yep. If you don't change how you're pressing the gas, it'll still continue at the same RPM, and it'll have the same frequency. It'll have the same period length. Now here's the other thing about this, is that all functions, not just these, not just periodic functions, not just anything else, all functions can also be used, or we can use y equals a times f of b times quantity x minus c plus d to do function transformations. These are the basic ones. So we have a linear function on the inside and a linear function on the outside. So the linear function on the inside is dealing with our x's, so b times the quantity x minus c. And our linear function on the outside is dealing with the function itself, so a times f plus d. And the way that you make it work is you say, okay, well, what does a do, right? It's a multiplication on the outside of the function. So if we're taking a function value that's coming out of the function, that's our y values for the function. So then if we multiply those y values by something, we're going to take the distance that it is away from, in our original functions, 0, right? If you multiply 0 by anything, it stays at 0. If you multiply it by 2, if you multiply any of those function values by 2, then their distance to 0 is going to double. So here, this is a multiplicative scale factor. And it's specifically vertical. So I will often call this a vertical stretch factor. So in this particular function, we see that it's going to take all these values here, and it would, if it's like 2, for instance, then basically all that's going to happen is our value here, which is the top, is going to get multiplied by 2. And all of the intermediate values are also going to double in size. So this thing at root 2 over 2 just becomes the square root of 2, because you just doubled it, right? It'll be 1.4. And then this one up here is going to be at 2. This one's still going to be at 0. This one's going to be at negative 2, negative root 2. So our vertical stretch factor is also known in terms of trigonometric functions specifically. This is also what's known as the amplitude. So you probably heard of amplitude modulation, which is one of the options that your stereo, your radio has. It is receiving signals from in the radio spectrum, which have a particular frequency. And then what it does is it reads, okay, of all the stuff that's coming in on that particular frequency, it's going to change its vertical. Hey, Edzu. Good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're currently discussing, what is this? Function transformation, and specifically how it relates to trigonometric functions. If you have any questions, let me know. Okay, so our multiplicative scale factor is going to talk about the amplitude of these waves. And so your amplitude modulation radio is looking at all the stuff coming in on a particular frequency and saying, how is it changing its amplitude? You could set it for like a particular level, whatever it is. And when you turn the knob on the radio, it picks up the stuff that's at a particular amplitude, and then it looks at the I might be wrong about it. It might be that it looks at the stuff, it looks at its frequency, and like that tells it how to spit out the signal in terms of what it sounds like. I don't remember exactly how it works, but that's what your amplitude modulation is doing. Your frequency modulation, your FM radio, is looking at stuff that's coming in at a particular frequency, and then the amplitude is telling it how loud to be for all of its particular sounds. So it's all really cool stuff, and I don't really know enough about it to really get it, but working on it. So oftentimes we do have a Discord server that is here. This is Penn Center's Discord server, but we all kind of use it. If you go to the either Maths Forum or Maths Chat, I am currently there, so, or at least I have it open. I can take a look and check things out. Yes, waves are a little important. So it's not until you get into like differential equations, which is beyond Calc 2, that things become like absolutely super important in terms of like, how do you build an electrical circuit? This is all 100% dependent upon this trigonometry and calculus that we've built over, millennia at this point. One of the other really big things was that we, yeah, and like computer engineering would require more, specifically talking about like RCL circuits and things like that. Computer science, in terms of yours, is much more, I would suggest, probably algebraic based. And so like you want to understand mathematics to calculus, etc. level, but that's going to be slightly different. So you're not going to need it necessarily in terms of really. You're not always going to need it in terms of like, in terms of the very specific things that you're doing. But stuff like neural networks, AI systems, etc., need a lot of differential equations in order to understand how like all of the individual pieces work. Okay. And I've also done, my spouse and I did a lot of work. I shouldn't say a lot. Took a class for our master's level in neural networks. And so that was really cool to try and understand all of the little nuances that existed between like trying to build AI systems and differential equations and trying to figure so many things out. Definitely needed Calc 2. Differential equations was, you know, I mean, it was necessary for both of our degrees, but it helped understand like how to make this stuff work. Helped us understand that. Okay, our D here, and not quite there, is actually taking those y values that are coming out of the function and then adding to them. So here, if we took this 0 value and we just said plus 1 at the end of it, then that would take that 0 and move it up to 1. If we took at pi over 2, we get a value of 1 back, plus 1, it adds 1 to it, makes it 2. Okay, and then this 0 moves up to 1, this negative 1 moves up to 0. So everything is equally moving up one space. So this is going to be a vertical shift. And you notice that around y equals 0, what we really see for these functions is that this is essentially a line of symmetry, not 100% like it reflects over, but the stuff that we see above and below are equally balanced. So this becomes what I call the midline of the function. Right, so y equals d. So this is going to be called the midline of the function. That's what I call it anyway. Okay, and then when we take the stuff from the inside, our b some of this stuff gets a little bit harder to see, like what exactly is going on. We may have to do an example, but if you were to multiply the inside of the function by 2, right, what you're doing is you're taking the x value and you're making it twice as large as it should be before finding that value of the function. So you're saying like, okay, I'm going to treat this point as if it were twice as big. And that value over here is going to get dragged back to where we are currently. And over here it does the same. So let's say from 0, right? If you multiply 0 by 2, it's not going anywhere. So that doesn't change anything at the center. But anything that is negative, we double its distance, look at its y value, and then pull it back over here. Any positive x values, right? We find its x value, find the distance. Nope. We find the x value, double its distance, take that y value, and bring it back here. So in either case, it's taking the stuff that's out here and essentially having the distance until we get to that point. So in this particular case, if we use a large value for b, we're going to cut the distance by that factor. So this is a multiplicative scale factor in the horizontal direction, but in this particular case, we're doing a horizontal compression. I'm letting the words do the work here. So if our horizontal compression factor is 2, then it's going to compress the function by a factor of 2. So all of our distances end up getting halved. If our horizontal compression factor is 1/3, then we're going to compress this a third as much as we were just holding on to it. So it gets relaxed. And all of these values then, the distances to their original x values, to their points, get tripled. All right, and then C kind of does the same thing. If you add 1 to a particular number, right? We're starting here. We add 1 to it. Then we find its function value and then move it back. So our whole function is moved this way. If you add 1, everything gets shifted back left by 1. If you pick this value and you subtract 1, then you're looking back 1, taking this function value and then pulling it back over here. So this is a horizontal shift. But the weird thing here is that it's in the opposite direction as our vertical shift. And let me check on EdZoo here. Yep, there it is. Circulation of a fluid with velocities, u sub theta of r. Good times. I may not be the person to do this one exactly. No, you're fine. Okay, it's a circle. So that's good. When you say does not include the origin, is the origin completely outside of said circle? I think I'll be able to, might be able to get something. We'll see. Okay, so our vertical shift is going to be the same direction as the sine. Our horizontal shift is going to be the opposite direction as the sine. This is sometimes known as phase shift. However, really, phase shift is b times c. So if you were to distribute the b into both the x and the c terms, this would tell you the amount of shift compared to the period, which is really distracting, and I don't like using it. So most of the time I just go with, okay, look, this is the horizontal shift, it's C. So if it says x minus 1, your horizontal shift is 1. That's it. The reason that I do that is that, again, we're just talking about a distance. Just talk about the distance. If you talk about phase shift, that's specifically talking about compared with the period And again, it gets hard to discuss it. Meh. Our horizontal compression factor also tells us what the frequency is. So how many more times are you going to go through the same motions as the original function in the same amount of space? So if it's 2, then you're doing 2 periods within the space of one usual period, one typical period. If it's 1/5, then you're doing 1/5 of a period within the usual space of one period. So it gets pretty cool when you start talking about this stuff and you can't see what I'm doing. Talking about this stuff and saying like, okay, let's do like, I could put in an A, B, C, and D almost immediately. And you should, in theory, be able to come up with the values that you need for it like very quickly. Because if you do it the way that I did it, what you're going to say is, okay, where is my, and in my pre-calc classes, we start from the very beginning of class doing this. Where's my origin point? Right? The place where it's usually 0, 0, where has that been moved to? You just have to find the 2 shifts. How much has it been moved over and up? Done. There's where the origin point is. This one, slightly harder. It's not actually on the function, but it's here. Right? How far has that point been moved over and up? It's your shift in both directions. Right? Move that. Then you say, where's my initial point going to be? Well, that's this one. So the initial point for this kind of function is going to be starting from wherever your shifted origin point is, it's the amplitude beyond that. If it's positive, it's up there. If it's negative, it's down there. Ta-da! Like it's not particularly difficult. And then you say, oh, now we just go 1 period away and mark it again. And then go halfway. We know that that one's on the opposite location. Halfway again, it's at the zeros. Halfway again, it's at these quarter points. I can do an example in a bit, but just for a second, let me try and answer Edzu's here. So nope, circle. Well, even if it's not. Oh. Thank you for keeping me hydrated. Okay, so let's just assume that this is any sort of closed figure. It doesn't have to be a circle at first. We're saying that it does not contain the origin, so the origin point is here. And DC, or DS, is going to be any segment that is going to look at like what is the overall, you said it in here, what is the circulation of this fluid within this segment? And then we're going to sum this up over the whole thing, which is the same as taking the integral. Okay, so it's either, so gamma is going to be equal to the integral around some particular surface or curve. I don't want to use surface. Around some curve, Now it does happen to be a circle in the other case, but we'll do it in general first. Of u times dc. C's lowercase. Not like it really matters, but you know. Maybe. Okay. So the way that you have this here, right, I'm going to let this be, let this location be theta equals 0. And probably also 2 pi. Alright, just to say that we've gotten around back to the same place again. I have no idea if this is right, by the way, just letting you know, disclaimer. I have not done this same type of stuff since Calc 3, so we're talking like 25 years. I have looked at my engineering mathematics book occasionally, so there's some of that in there, but I'll have to see if I actually kept it. Okay, so this is going to be the curve that we're concerned with. Now I think the way that this works is your u sub I is being multiplied by the distance along the curve. Yeah, dot product. Okay. And I don't know what your DC vector is. So it seems like it should be the vector that you are moving along from point A to point B. So C sub I vector. Ugh. And then U is going to be the flux across that vector, essentially. Dot 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 question mark. So we'll get rid of the D that's down there because it's really just the, again, C vector for that one particular location. And then your U is really a U sub I vector because it's one single one, and we're doing an infinitesimal number of spaces. Okay, so if we do a dot product, U sub theta of R is equal to omega R squared, or is equal to V over R? Or are they two separate things? Constant, okay. And V over R? Okay, so these are two separate velocities. Okay. As in two separate examples? Okay, yeah, okay. So, okay, so this means that we're doing from 0 to 2 pi in order to go around the whole thing. Okay, so I would probably say you want to parameterize this. You're doing it on theta. Looks like a happy face. Omega r squared 0. So that is theta RT. Okay, so your omega is just a constant that comes out. R squared times dc. Your r squared is going to be done in terms where, yeah, r is going to be in terms of r as a function of theta. And if you want to do this as a function of theta, there's curses. It's the sine of theta, or the cosine of theta, but you need a way to shift this out, right? So we want this as a function. All right. So function transformation, like we were talking about in the other one. When you were doing like x squared plus y squared equals 1, okay, r squared, just generalize. So this is a constant, right? It's just the radius of the circle itself. If we want to parameterize to r and theta, then our x and our y here need to be changed to r cosine theta and r sine theta with asterisk squareds. So this is squared, 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 squared. Right, it's r Jesus. But. Now I can't remember how to do the frickin'. Hang on. We wanted this to be, let's shift it 2 away. So this is now going to be, that's different. Okay. This is now going to be parentheses r cosine theta minus 2 parentheses squared. So we can get r squared parentheses cosine squared. Yeah. I was just kind of like throwing something out there. Sine squared theta, this is going to eliminate to become 1. And then this is going to be a negative 4r cosine theta plus 4. Plus that is equal to whatever our constant radius is. Whatever the radius of the circle that we actually want is. Okay. Sorry. Let me come back to this in just 3 minutes. Sorry, gotta cycle water again. This is getting crazy. Alright, be back in 3. All right, hey everybody. Yeah, I was doing a specific example instead of generalizing, but you know, yeah, generalizing will help out. Oh dear, I broke it. Okay, no, okay. X minus a squared plus y minus b squared equals rc squared, because it's just a constant. Yep, so r cosine theta minus a plus r sine theta minus b squared equals rc squared. And now, this was something that I did not bring up when we were talking about the functions up top, which is what their actual names were. So yeah, the curvy functions that you were talking about before are the sine and cosine function. We know them from geometry as the ratios between A, B, C, theta. Right, so sine of theta is going to be the relationship between the opposite side and its hypotenuse, and cosine of theta is going to be the relationship between the adjacent and the hypotenuse, so A over C. So that's one thing we didn't actually bring up, but that is, the name we use for these particular things. All right, this is r squared cosine squared theta minus 2ar cosine theta plus a squared plus r squared sine squared theta minus 2br sine theta plus b squared is equal to rc squared. Okay. Again, this and that. Cosine squared plus sine squared is 1, so we just get r squared minus 2ar cosine theta minus 2br sine theta plus a squared plus b squared. All right, we've got a quadratic. Yep, absolutely. All right, and for the other trigonometric functions, we also get something else that isn't often brought up in many of the classes. So let's see, just real quick, can we get anything nice out of this? R is equal to, this is a gross this is a really gross quadratic, but I mean, technically, if we want it as a function of only cosine and sine, or as a function of theta only with a bunch of constants over there, yeah, it's possible. So this is going to be a negative b, so 2a cosine theta plus 2b sine theta plus or minus square root that grossness squared minus 4 times 1 times c, a squared plus b squared minus rc squared, all over 2. Yay! Well, there you go, Edzo. Gross. So the function we can use here is going to be r equals a cosine theta plus b cosine theta plus or minus this square root thing over 2. We're not going to get... Oh, no, we are going to get a 4 out of it. So that's good at least. The 2 at the bottom and the 4s on the inside will divide out. So forgive my shorthand. Fun. So that's going to be a... no, okay. That's not there. A cosine theta plus b sine theta parentheses squared. Yeah, it's a negative technically on the inside, but it gets squared, so that's... doesn't matter. Minus parentheses a squared plus b squared minus rc squared. Why are you welcoming me back to my own chat room? Weird. Okay, so in terms of our other trigonometric functions for NEP, this is something that gets a little weird, but so first of all, when we're looking at theta, we're also technically looking at this extra section here, which we can call theta prime. So this is, in this particular case, it's a supplementary angle. It's the thing that adds up to make 180 degrees when you start with your theta. It's not really important. What is actually important is that no matter what quadrant you're in, the angle, theta, is always going to start from 0, your positive x-axis, and then work its way around counterclockwise until wherever the terminal side is. The angle that you make with the x-axis, however, right, if this here is alpha, then this angle here is going to be alpha prime. It's the angle that you make with the x-axis, no matter where you are. These are what are called reference angles. There we go. Been a while. right? So if this is beta, this is beta prime. And then in quadrant 1, your, gamma, gamma and gamma prime are going to be the same angle. So we just don't bother. But in quadrants 2, 3, and 4, you always create an angle with the x-axis, and that's your reference angle. And the values you get for those are always going to be the same as the original angle theta. They may be positive versus negative, etc. You just have to think about, well, what is it that I'm really thinking about, and what quadrant am I in? So do I care about my y values, like my sine function? Then, up is positive, down is negative. Is it my x values that I care about? It's going to be right side positive, left side negative. All right, so then other trig functions. There's a couple of ways to deal with this. So let's deal with alpha here. So one is the tangent of a function. And so when you think about tangent, hopefully you think about like this thing, where we're making a tangent line, making a line which is perpendicular to, that's pretty good actually, which is perpendicular to our terminal side. And Edzu, let me know how this is going. What we can do with this. Alright, so there's a few different things we can do here. One is that this is going to make right angles with the tangent line and the terminal side. We have alpha prime, which is our reference angle compared to alpha in the third quadrant. And the length of the tangent line, which goes to the horizontal side, should be the size of our tangent of alpha. Trusting the process. Yeah. Love to hear it. Yeah, I'm getting kind of stuck in terms of like what to do with this. If it's, oh. We're taking the integral of r squared. There's going to be a cross term which has... There's going to be a cross term which has a cosine theta plus b cosine theta times the square root of that stuff. That's going to be really gross. It is possible that that's going to include a it's possible that that's going to include a like secant or something like that, whatever the integral of x root x squared whatever it is it's going to be. I know that's not really helpful. Sorry. So what we actually can do here uh, okay. Yes. Yes. Okay. Um, so if you were within some sort of rotational vortex, I think I got it now. This is similar to something that we did in complex analysis. So if you were to start somewhere and then you were to like make a root, again, it doesn't actually matter what shape this is. You would have had to do the same amount of work with your engine to work with the current going in one direction versus against the current in a different direction in order to get back to the same place. So you would have had to do the same amount of work in every single direction in order to get back to the exact same place. If you decided to just kind of like go with the flow, as it were, start here and then go around the origin point, then you're doing a lot less work overall. You could, in fact, like just turn the engine off and let it go around in a circle around the origin. Now, whatever actually is going on with the circulate, I don't know, whatever. But it would have, like, it would have taken you a non-zero effort. In other words, this is like when you're talking about work, right? If you pick something up and then put it back down again, you've done no work, but obviously your muscles don't agree. In this case, right, if you're doing... If you have turned off your engine and you just go with the flow around in a circle or whatever shape this is, then ended up back in the same place, then that is the circulation. Like the amount that you've traveled could be thought of as the circulation for this. If you went out into random space and made a circle out here, or any other shape for that matter, you do any sort of shape out here, which is not including the origin itself, then you have, again, gone around in that shape, and you've done the sum of all of the pieces of that end up becoming zero. I get it now. Okay. Hey, Don. How's it going? Everything go pretty well on your end? Saw some DayZ was up for tonight. Doing some murders. And NEP. So when we're talking about the tangent, we don't actually know what the tangent is yet, but if I were to convince you that this is supposed to be tangent of alpha, right, then we could look at this in terms of our radius and the thing that I said is tangent of alpha. And then I could also create a similar triangle here where we do know that this is our y value and this is our x value in terms of its distances. And you can see, right, the x and the y are the horizontal vertical distances of this particular triangle. They are the two legs of our unit circle triangle. But if we look at the big one with tangent, these are also the two legs, the tangent of alpha here and r here. Then we can set this up as a proportion, which says that the tangent of alpha divided by r, so this is, as we know it, opposite over adjacent, is equal to opposite over adjacent is y over x. Realistically, we could also say, well, this has been scaled up by a size of r, or we can scale it down by a size of r to let it be just the radius is 1, in which case this stuff just goes away, and we get that the tangent of alpha is equal to y over x. This becomes a super important result. Whole mess of polar coordinates? Yeah. Yeah, we were looking at Edzu's question was about circulation. And so if we look at the circulation of a particular the circulation of a fluid with given velocities u sub theta of r being whatever they're going to be, where the curve C is a circle that does not include the origin. And Edzu was saying that if the book says that if the curve does not include the origin, doesn't even matter what kind of curve it is, if the curve does not include the origin, then the circulation is 0. And I was thinking about something in complex analysis, which basically says the same thing, where if you make some sort of path, a closed path, that is not including the origin or a particular pole, then the curve integral is going to be equal to 0. Irrotational vortex. Okay. Okay, so it can't be like what I drew with the green. It can't go just around in circles like that. This would have to spiral out or spiral in, potentially, to a particular place. And the equations that you gave were going to be some factor times r squared. So that's not a rotational vortex. And v over r, which also should be irrotational, I think. So Calc 3 in most places is vector calculus. So I would agree that that's probably what this is, in terms of like American numbers. The Splooey! Hey, how's it going? My name is Obi-Wan Pez. This is N-Simplex Pachinko. Good evening. Welcome. We're doing some math tonight. We're kind of all over the place at the moment. We're doing some vector calculus, talking about circulation measurement, and we're also at the very top left or top right-hand corner there, doing some definitions of trigonometric functions. Holy crap! It's also 2:38 in the morning, so I should probably sign off pretty soon. Yeah. Yep. Yep, if you're using a quarter system, that also typically happens. It all depends on a number of factors, including where you are, what program you're in. Okay, so then there's two other major... No, that's a lie. There's a bunch of other measurements that we have here. So what we have over here at the top end, it's the distance between our origin point and where the tangent touches the x-axis. So that distance sideways here is going to be called the secant of this particular angle, alpha. And again, we can set up a proportion between those two triangles. So the secant of alpha is the hypotenuse of that outer green triangle. And we could put that over r, being the radius, which is the adjacent leg to alpha. Or in this case, alpha prime, which is our reference angle. And then similarly, right, so secant alpha over r is going to be equal to then, on the smaller inner triangle, that was our adjacent, nope, sorry, hypotenuse over adjacent. So r over x. Again, if this is scaled up by a factor of r, then we just get r secant theta over r. So these end up dividing out, and we get r over x is our secant of alpha, or 1 over x if r is just 1 around a unit circle. So we end up with secant of alpha is r over x. Tangent of alpha equals y over x. And then we move to the lower triangle, which is defined by that right angle and these three sides here. So again, our radius, the part that's along the y-axis, and the part that's along the tangent, but in the opposite direction. Here YW, hello. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're doing some math tonight, talking about right now. Just this is last little bit of trigonometry. It's not terribly difficult. It's just really unorganized right now. I deserve it. No, that was actually good. I want to keep that where it was. If we get rid of that and that. That bit. Again, we do this. We do this. And then we draw in our angle, a tangent to it. It's pretty close. Okay, and then draw in the rest of that line. Okay, so we had a right angle here. Again, this is our alpha prime. Our actual alpha is here. And interestingly, right, by congruent triangles, or sorry, similar triangles, this angle is going to be alpha prime as well. We had a radius. Now, this is where I curse you having used all of these different notations everywhere. Right now, what we're actually doing is we're going to look at the tangent, but it's not to alpha prime anymore. It's the tangent to this angle here, which is the complement, there we go, which is the complementary angle to alpha prime. So what we're going to do is get the complementary tangent of alpha prime to be this distance here. And yes, it is known as the cotangent. Similarly, we're going to look at the distance along here, which is going to be the secant to this orange angle here, which is again the complement of alpha prime. So this was the secant of the other one of just alpha prime. So this is going to be the cosecant of alpha prime. I mean, all those assessments can be true. It's just a matter of perspective. So again, the tangent of that particular angle was the length of the tangent line to that particular angle. We make a physical tangent. just the process. Oh no. So we build an actual physical tangent to that angle along that edge of that circle. And then on the other one, the orange one, we do the same thing. It's just that, what angle is it? Oh, well, it's not the angle we wanted. It's the complement of that angle. So we call it a cotangent. Complementary tangent. All right, so when we go through this, then we've got our same original triangle way in here that had our x and our y values. And then this is a similar triangle to the big one we just created here. They're all similar triangles. So when we build out these similar triangles, then we say, how do we relate the sides to each other? Okay, we get, well, the cotangent of alpha prime compared to r are going to be the two legs of the triangle. This is the adjacent cotangent of alpha prime is adjacent to alpha prime. And then r is opposite alpha prime. That's going to be equal to, we go back to the small triangle, which is here, and we say that the one that is adjacent to alpha prime is x, divided by the one that is opposite it is y. And again, this was scaled up by a factor of r, so r cotangent, just forget that, ends up being cotangent of alpha prime is x over y. So I am actually from, man, it's been a long road. I am currently streaming from the UK, which is why it is now 2:50 in the morning. Uh, let me tell you, math is one hell of a drug. Um, wake up juice. So I'm actually coming from Maryland in the United States, where I've been teaching for the last 15 years as a associate professor of mathematics at a 2-year college in Maryland. And then before that, I came from New Hampshire. So I went to the University of New Hampshire. And yeah, doing a lot of moving around and crazy stuff like that. All right, for the cosecant, we're doing the same, like divide by r. That's going to be our, this is the hypotenuse divided by our opposite. So the hypotenuse of the small triangle is r, divided by the opposite side is y. Again, this is scale up, so we get rid of those r's there. So our cosecant of alpha is going to be r over y. So that's how we get our other 4 functions. We could do the same for our sine and cosine in order to understand where those are coming from. Oops. Alright, when we do that, this is y, this is x. This was our alpha prime. And our 1 there, r. So here we talked about our sine function being the ratio between the opposite side and the radius, and then our cosine of alpha prime being equal to x over r. So this is the way that all this is working in terms of like whereabouts we're putting it, what ratios we get when we look at the relationships that exist between all of our side lengths. And man, I can't put this anywhere good. All of our side lengths. Man. Ratios of side lengths of these triangles. Well, thank you. Yeah, so like this stuff again is not particularly hard. It's just dependent upon your individual understanding of where these things are all coming from and where they're going to. So we'll talk more as we go through this. I'm gonna have to I'm gonna have to quit, but just for the night. So I will definitely stream more about mathematics. Anybody who wants to come in, say hi. We'll talk about cool stuff. And I don't know exactly when I'm going to be streaming math next, but yeah, probably fairly soon. Yeah, well, let me know what you are interested in learning about, and one more time we'll shout out other math streamers who are possibly on right now. These are the 7. Don does math, dropped in just a couple minutes ago. Zach, e to the 2i pi. Penn Center, Ian Stuckey, who rated in earlier, thank you so much. Obi-Wan Pez, that is me, at nsimplex pachinko. Danny Highway and Dr. Gold at Actual Education are our kind of like core 7 streamers who are getting together and trying to do cool stuff, be math people, play some games together on usually weekends, but we'll see how it goes. So again, thank you so much for coming on in. We'll see if anybody is currently on. I should have actually just typed live. Yes, Penn Center. So we'll go see Penn. And if anybody wants to ask any questions in there, you can also ask in his Discord. I will shout that out as soon as I get over there. So thank you very much, everybody. Good night. This is Obi-Wan Pez for nsimplex pachinko. That did not pop up. Oh no. Is he not allowing raids? It is possible he's not allowing a raid. Hang on one sec. If he got like some sort of problem, there is the possibility. No, it says start raid. Oh, okay. It says we're already raiding Penn Center, so we're going to go like this, /unraid. Raid has been canceled. Okay, let's try this again. We're having some problems here, apparently. Yeah, paste your favorite theorem in chat. Yes, absolutely. We're having problems, apparently. So if anybody is... Well, that's going to be a problem. Apparently I'm having a problem with this web page for some reason. Hey, there we go. I just had to refresh. All right, so anyway, thank you very much, everybody. We're going to head on over to Penn's channel. So thank you very much. This is Obi-Wan Pez for nsimplex pachinko. We'll see you next time. Did you also not do that? Are we... We're apparently having some problems.